Tape settings. Ah, there we go. Pog. There we go. Okay. You put that into the live chats. There we go. Let's see if it works, first of all. Oh, I forgot. Doesn't look like it. Well, that's okay. I really don't care. Oh, what the fuck? Nope, wrong one. There we go. I do not know what happened. I think I'm gonna be here the whole time, but you're telling me you don't want to learn how to do implicit differentiation? You don't? Ah, crazy. I mean, then again, like, this is about 15 minutes, 15 minutes, 15 minutes, 13 minutes, and then 22 minutes. You tell me you don't want to be here? Oh, what? Crazy. But I mean, yeah, that makes sense though. But like, I mean, that does make sense. Like, come on, man. You know, it's either you learn this right now, or I'm gonna have to teach you it in the middle of a school year. Come on, make my life easier. I'm just kidding, bro. Definitely not. I'll stick around for a bit. Okay, but thank you.
Welcome to section 4.2 BC Calculus.
I've already learned a
we are
bit of
learning
this.
a special
I wasn't supposed to, but I did.
technique on how to take derivatives today, known as implicit differentiation. And I know that our brains are swirling with all of the derivative rules that we have learned so far.
Not really.
If you think about what we've done in the previous chapter and so far in this chapter, we've learned the power rule, the product rule.
Oh wait, shit! I just realized. Everything's good right now. Fuck it.
The quotient rule, the chain rule, right? And ways in which to communicate those in terms of velocities and accelerations. And I know that some of us might be thinking, oh my goodness.
I'm starting a drone course in 3 days for the next 2 weeks, so I'll be doing my own thing. Okay, makes sense, makes sense. Let's go. I hope it goes well. Hey, Nick. Hey, Murphy.
What do I
hey,
need
how are you?
another derivative technique
How are you on
for?
this fine day?
Well, I am here to tell you this cool thing called implicit differentiation
Roman. How are you?
is really built to help us with a family, well, numerous families of curves of what they call implicit curves.
Oh.
Now, how do you identify an implicit curve? Basically, it's a curve where it is either very hard or nearly impossible to get y by itself, okay? So if we think about it,
I'm tired, but good. I'm
if I were
glad
to create a
you're
couple of quick examples
doing
like
pretty okay. Just vibing, you know.
this one right here. This could be an implicit curve if you wanted it to be, but it certainly doesn't need to be, because in this curve it is fairly simple to get y by itself. We could simply subtract over the 3x squared, also add over the 7x, then our curve would look like this, and all we would have to do is divide everything by 2. And so we would wind up getting an expression that looks something like this, okay? And because it was so easy to get y by itself, now we can just go and look at our traditional rules. In this particular case, we don't even need a product rule or a quotient rule or anything like that. We can just simply use the power rule.
Oh, that's awful.
And we will have the derivative of this thing in short order.
It'd be like negative
specifically, the derivative is going to be notated as dy dx. We drag that 2 down and multiply, we get negative 3x to the first. And this is really just a 1, so if we take the derivative, we wind up with 7 halves, okay? So again, this one is not considered necessarily an implicit curve because it was very easy to get y by itself, and then we could just take the derivative in a more traditional manner. You guys, there are many, many curves out there that is not the case for, okay? Part of what I also need to introduce to you here, however, is a little bit of why it is that we even use this notation dy dx. I wonder if the back of your mind you were kind of thinking all along.
Well, okay, wait, hold up. It was because like you take the derivative of y and then you divide to the derivative of x, and that's your like if I remember correctly.
That's kind of crazy notation, and where does it come from? Literally taken, what this means is the derivative of y with respect.
Oh fuck, my bad.
To x.
I don't even know what the fuck that means, bro.
And if you guys think about the expression that's been given to us up above, at the point where we got to y equals negative 3 halves x squared plus 7 halves x plus 9 halves. Okay, think about this. Technically, the derivative of y under the power rule is really just the number 1. But what we're doing is we're recognizing that we're taking a derivative on y in an equation that is generally with respect to x. Now, that being said, technically there's a bunch of other little tiny notation going on here as well, you guys. So when I drag this down in front and I use the power rule to call this negative 3x, technically I should also be recognizing that this is a derivative on x with respect to x. But of course, that just generates the notation dx dx, which is just 1. So nobody ever bothers to write that down. The same thing that would happen here. The derivative of 7/2 x is just 7/2. Technically, we should notate that it is a derivative on x in an equation that is also with respect to x. But again, both of these just wind up being 1, so that's why you never actually see them in the equation.
And that's it.
Now, you guys, I do understand that me sort of explaining that has been a little confusing based on the way that we are used to taking derivatives, but I think it's important to recognize that up until this point, we have always taken for granted the fact that the y could be easily by itself, or most of the time was already by itself. And as we moved through taking the derivative here, we were always taking derivatives with respect to x, okay? We need to understand now that what's really happening is y is being taken with respect to x, which is why we need this dy dx notation, and the x's are also being taken with respect to x, so we have dx dx notation. What does that really mean, and how do we really use it? Well, let me show you an example, and what I'm trying to do here, you guys, is blend together this upper idea of what really is an implicit curve, and also how do I use this dy dx and dx dx
y squared
plus
x squared equals 1.
Okay?
I swear to God.
So let me start with kind of what I would think is a simple example here. Let's say the implicit expression that's been given to us here is something like this. Okay?
Oof.
And I want you to notice that getting y completely by itself here would be a bit challenging. In fact, you'd have to do like completing of the square with this and do some factoring in order to eventually get the y by itself, and nobody wants to do that, okay?
What?
I mean, a person could add 4y over to the other side, but then you have a mixture of y's on both sides, and you have not really gotten y by itself, so that's not really going to work, okay? So instead, implicit differentiation allows us to do the following. And again, I know it's confusing at first, but after you guys get used to it, I really think that you're going to fall in love with it, okay? We're going to march through this equation one term at a time, and we're going to be taking derivatives with respect to x, using the power rule mainly, okay? So the derivative of y squared would be 2y, but I need to attach a dy dx to that, again, to recognize that he is a derivative on y in a world where x is the primary variable.
I need to write that better.
Let me do the next one.
Oh, you're just not going to pause when I hit spacebar? Bet. So it goes 2 dy dx.
4y would be 4, but again, because it was a derivative that involved a y, I need to attach that dy dx to recognize that. Under the power rule, the derivative of 3x is 3. Technically, what I'm chaining on to that is dx dx, right? But nobody ever really uses that because it's just a form of 1.
Plus 0 because
and good news for us, in the world of implicit differentiation, regular numbers still just disappear to 0. Yeah. Poof, they're gone, okay? In the next step, anything that did wind up being a dx dx, which is really just 1, we should really just ignore it at this point, because multiplying by 1 is not going to change a darn thing in the way that the rest of this equation is written, okay? I think the next thing we need to recognize is the fact that dy dx conveniently wound up being a common term between both of these guys, okay? So I can factor it out as a common term.
What the So you treat it as a variable. Okay, bet. 1 second.
And that would leave me with parentheses 2y minus 4 is equal to 3. And I'm here to tell you that we can call ourselves finished with an implicit differentiation question once we have dy dx completely by itself.
Oh, shit.
So right now I want you guys to read the fact that this reads dy dx times a certain parenthesis unit. And of course we know the opposite of multiplying something is to divide by that same thing. So we're going to divide by the quantity 2y minus 4 and make it cancel. Algebraically speaking, this allows us to get dy dx by itself. Okay.
What?
Minus 4. And there it is, you guys. That is the final answer for our derivative.
Oh,
the other thing we need to understand is these derivatives still just represent a slope.
Yes.
So if they wanted you to find the slope to the curve at, and I'm totally making up this point, you guys. I don't even know if this point lives on the curve, you guys, but I'm just making it up right now. Let's say that they want you to find the slope at the point 1, 3. I want you guys to think about the fact that in the past, it was usually the x value of the point that we wound up plugging in to figure out that instantaneous slope. And the reason why that always worked is because your derivatives were also in terms of x. But I want you to notice that this time, your derivative is in terms of y. So if you want to evaluate the instantaneous slope, you would have to plug in a y value of 3 there. We don't have any x's in sight in this final answer, you guys. So we would have to grab for the y value of the point in order to find the slope. Okay.
That's awesome.
Let's look at another example. And this time, I'd like to shortcut the example just a little bit by saying the following. Any time that we take a derivative that is with respect to x, we can think mentally that there's supposed to be a dx next to it, but I don't know that we really need to write it down, you guys. The way that I have taught this to my students in the past is basically saying to them, x is the king. He is so special that when you take his derivative, he just does that derivative like he normally would, okay? The y's are not special. The y's have to have these extra things attached to them in order to recognize that y is not the primary or the special variable.
My bad.
Okay? So let's take a look at another example, and we'll try to use those ideas here to help us out a little bit. Let's say that we have something like x cubed plus y cubed is equal to 2x plus 5y, okay? And really keep tucked back in your mind the idea that the x is the primary variable. So his derivative can be taken like we have always taken all of our derivatives.
So it'd be
the y's are the ones that are going to be problematic for us. So here's what I think my brain is thinking.
No, chain rule it.
Under the power rule, the derivative of x cubed is 3x squared.
Yes.
And again, he's special because he's the primary variable, so he gets just to stay that way.
3y,
the derivative of y cubed
dy,
under the power rule is 3y squared. But y is not the primary variable, so that's why you have to attach the dy dx
equals
to recognize that we have taken a derivative on y with respect
dy
to
dx.
Moving on to the other side of the equal sign, the derivative.
How come, Murphy? Well, okay. Well, it doesn't help that you don't know. You don't know the power rule. You don't know. It doesn't help that you really don't know anything. The power rule is the simplest thing in calculus. It's such just a nice thing. It's so nice. It's basically like factorials work, but it's also really nice. It's how you find the slope at any point. Like, let's just say, 1 second. I'm about to move my camera and shit. Oh my god, things I do for people. Go home. 1 second. Just gonna do a little womp womp. Oh, just gonna do that then. Womp womp. What? I don't know anything. Excuse you. Well, okay. Oh fuck. What equation was it? It was such a good. Ah, fuck. Section 3.1. No, it was section 3.2. Section 3.2 was good. Wait, no, wasn't section 3.2? That was continuity. No, that's not a good one. God damn it. Man, I don't remember this one. Was it? There's no way it was section 3.3 was a good equation, because that was like really late. The power will define the derivative. Man, fuck it. I don't know. I don't remember one of the equations. What do you mean? Boom. My bad. My bad. My bad. Anyways, back to the video.
2x is 2.
I mean, yeah. It's mostly just knowing previous stuff. Because, like, what we're doing right now is just, like... Murphy, I don't want to hear it from you. It was like... it was really early on compared to what I know today. Because, like, the power rule is very nice. The power rule, it's spicy. It's nice. But, like, you know, this stuff, it's okay.
And again, he is your primary variable, so you can just leave it like that.
Trust me,
And
once
the
you
derivative of
understand the
5y
previous
would
stuff,
be 5,
you would know
but
it. You would
that
understand this a lot
derivative
better.
involved a y value, so we want to make sure to attach a dy dx.
Oh, yeah.
Okay.
No, you keep the y squared, then
In the
you
previous
dx.
example, this equation at this stage right here was already organized in such a way that the dy dx terms were already on one side of the equal sign. We did not get quite so lucky this time around, you guys. So that organization is definitely a part of what we have to do when we're doing implicit differentiation. I think of it this way. Anything that involves a dy dx should probably maybe be on the left-hand side, and anything that does not involve a dy dx winds up on the other side. So for this particular equation, that means that
never mind. What do you mean we? What? Bruh, never mind. What are you on about?
3y squared, dy dx is going to be over here.
Okay, yeah.
And I'm going to have to also subtract the 5 dy dx, right? So that our dy dx terms are on the same side of the equal sign.
Minus 5.
On the other side, we have the number 2, and I'm going to need to subtract him in terms of the 3x squared.
Yeah.
Okay? Again, this is just what we call the organization step of your implicit differentiation. You simply want to organize it so the dy dx's are on one side,
and then divide by
the regular
dy dx.
stuff is on the other side. The reason why we do that is because dy dx is a common term to both of these. And we can factor out dy dx as a common term, leaving us with 3y squared.
I meant, well, I was trying to say good luck. Why are you proud of me? There's no reason to. Oh, yeah, be dy dx of 3y squared minus 5 is equal to 2 minus 3x squared. If I could fucking write, oh my god. 2 minus 3x squared. 3! God.
Minus 5 equals all the rest of that stuff. And lastly, we are in a situation, once again,
but I fucked
where
it
this
up.
reads dy dx multiplied by something.
The reason shush, just
so
let me praise
the way
you.
that we get rid of multiplying things is dividing by things.
And then, okay, then you would divide by 3y squared minus 5. Womp womp. Womp womp. So then you get dy over dx is equal to 2 minus 3x squared divided by 3y squared minus 5? Yeah, womp womp. Yes, no! No.
And our final answer for this implicit, the derivative of this implicit curve, would look like this.
That's crazy.
Now again, let's pretend that they wanted you to use this derivative to find the instantaneous slope at a certain point.
Yeah, you would.
And again, I'm just going to make it up, you guys. Let's say that the point 1, 3 lives on this graph. I don't even know that it does, but we're just going to pretend. Notice this time your derivative is even more different than the one we looked at up above, because this derivative is in terms of x's and y's. So you would need to plug in 1 for x and 3 for y in order to reach your final instantaneous slope on that curve.
No.
The last thing I want to say, you guys, before we leave our first topic here, and again, the point of this topic was just to introduce to you guys when a person might need to use implicit differentiation, okay, and how to think of the variables in terms of dy dx and also dx dx and how we sort of express that, okay? Maybe you're wondering, this is the last thing I want to say, what kind of curves even do things like this? And you guys, if you look in your textbook in this section, the answer is there's a lot. There are figure 8 curves, there are spiral curves, there are Witch of Agnesy curves that maybe sit in the first quadrant and do something like this, okay? The point is that a lot of these curves are not functions, okay? They all fail the vertical line test.
Oh, shit, yeah.
And so to do the derivative traditionally, as what we're used to, those rules really only work on graphs that are functions, okay, you guys? But there are tons and tons of curves in our universe that are not functions, and we still need to be able to analyze things about the instantaneous slope of the curve at certain points. And that's what implicit differentiation really allows us to do, okay? So maybe think of implicit curves as frequently being curves that are not functions, but we still need to be able to talk about them in terms of rates of change or instantaneous slopes or derivatives. And so the use of implicit differentiation is what is required to do that.
Okay. I love how I just see this, like, bruh. And now we actually get into, like, high quality videos when I actually change my camera. Fuck. So then we get rid of that. We do a funky little this. 1 second. Boop. Then do a little bit of that. There we go. That's good enough. Gotta get rid of that. There we go. Okay, 1 second. Womp womp. Topic number 2. More complicated. Swear to God, I hate complicated shit. Bruh. Complicated implicit. These motherfuckers just has to say differentiation. Like, bro, that's such a weird and hard word. Tiation. Yes, complicated. We love that, apparently.
Topic number 2 in section 4.2. So now we've
The
been
fuck is
introduced
that?
to the basics of implicit
Oh,
differentiation.
okay.
We have the privilege of adding on to that things like product rules, quotient rules, and chain rules.
If I have to do the fucking chain rule instead of quotient rule, I'm gonna fucking drown myself. I swear to fucking God. I did that so much yesterday. If I have to do the fucking chain rule inside of a fucking quotient rule due to the implicit differentiation, I'm gonna fucking drown myself. Nah. Mm-mm.
And I would like to show you
Never again.
sort of an example of each of those right now in this particular topic number. So let's start with this one. And let's say we have this and this. And
18xy.
so we're looking out, like I said, for things.
Don't drown. Then don't make me fucking use a chain rule instead of quotient rule. To do, like, fuck. I had to do that for trig functions. Fucking. It's just so messy. I hate it. I just don't like it.
Like product rules, quotient rules, and chain
Let's say
rules.
saying 18x
And
times
I
y.
have to say, in my many, many, many years of teaching calculus, you guys, this little tiny product rule right here is a super sly thing that often gets by people, and they're not.
Now I have to take fucking physics, bitch! Fucking hate physics. Okay, fair, I understand. No, Muffy, you don't understand how messy it can be, because, like, you can deal with, like, you deal with, like, 4 different trig functions, because of the, you take the derivative of 1, and you sometimes get 2. Like, the derivative of secant is secant times tangent. Oh my God. And then it's like, oh, I have to distribute it, and sometimes you deal with x squared. You deal with, like, so many different variables. You're dealing with 4 trig functions, you're dealing with multiple x's, and you're dealing with fucking numbers. And then you have to distribute it, and then add it all together, and try to find common, and then, oh, reciprocals of each other. You got, like, do everything perfectly. And then, like, oh, what algebra step could I do now? Can I cancel out the 1 over cosine and the 1 over cosine? Yes, I can. Oops, I forgot that part. It's messy. The fucking... Never mind, I concur. I do not understand. Yeah. And then, God forbid, you do the and then the chain rule makes it even worse. Because, like, you have to deal with even more numbers than I just said. Because you have to deal with... Because, like, you have to make sure everything's in perfect order. You got to do the coefficient, do the sign. Then take the derivative of the sign. Then take the derivative inside the sign. So then you're dealing with 3 different things already. That's the derivative of the first. Then you take the second normal. And then you have to minus and then do the normal of the first. Then take the derivative of the second. All divided, but it's fuck off. It's ooh, god damn! And I always got so close to the right answer. So, like, sometimes I got 6 over 9, but the answer was 9 over 12. I'm like, I was fucking close enough. Like, no, the chain rule instead of quotient rule is awful, and especially with trig functions, it's worse because it's like, oh, cool. Trust me, it's awful.
Not really paying attention to what's going on. So we need to remember that a product rule
The actual fuck, I'm so confused.
Oh my goodness.
Trust me. If you knew what was going on, if you actually knew what I was talking about, it would make a lot of sense. I'll just... Fuck it. Okay. I'm gonna explain it very simply. Not Outlook, my bad. Where's Desmos? Okay, so let's just say that we have f of x. F of x is equal to sine. Let's just say we have that sine of x. Don't mind the graph, that's useless right now. And then we have g of x is equal to 1 plus cosine squared of x. Oh, fuck. Oh, it actually graphs it. Cool. I didn't even know that. And so we would have for the quotient rule you can only do this be cosine of x. I forgot it does that. Oh my god. Oh yeah, cosine squared. My bad. Fuck. There we go. What the fuck? Okay. So basically the chain rule states no, not the chain rule. So so then you would take the derivative of the top, like we call it f prime. So we would do f prime of x times the normal of the bottom, which is 1 plus cosine squared of x. And then we would have a minus there. The minus is very important. Very important. Very important. And then you would take the normal of the first. Let's put in parentheses to make it look fancy. What the fuck, what am I making over here? How does it know f prime of x? The fuck? You'd never know what to do. What the fuck? Oh, nah. And then we would times that by the derivative. Ah, fuck. Yeah, you'd have to do the chain rule. So you would take the derivative of the bottom, which then the derivative of the bottom, you would have to do the chain rule. So we put in brackets of 1 plus cosine of x, because, okay, the thing is, mathematicians are very lazy, so when it says cosine squared of x, it's saying that this entire thing is squared. So then we would have to do this squared. And then what would happen is that we do everything in steps, okay? Steps. So with the power rule, we would drop the 2 in front of this, so then we would get 2 to the bracket of 1 plus cosine of x, technically to the power of 1. I'm gonna make it nice. And then we would chain it on with that, and then we would take the derivative inside of that, and technically, to make it look nicer and actually make more of a chain rule that's better, you would do that. And so then you would do fuck. And then technically 1 would be 0. So it's useless to have that. So then we would just have cosine of x would be minus sine, and then you keep the x in there. And then you would finally do the derivative inside the cosine, which is x, which is just 1. And then you would technically want to bring that 2 to the 1. So then you get this. This is the final result you get. You get 1 plus cosine of x, technically to the power of 1, even though it's useless to have that, times the negative sine of x. And that's it. That's the derivative of that. And so since we know this now, let's bring it to original function and put that in. So we would have 2 of 1 plus cosine of x. This is a horrible notation, so I just dropped the 1. I didn't close the 2 out yet. Okay, good. Times negative sine of x. And then this would all be divided. Fucker. Can I just copy and paste this, please? Can I? Oh wait, I forgot to put that there. What I need to do also is the derivative of sine of x is cosine. So it'll also have another cosine of x times this. Can I just do this, please? all divided by the bottom function squared, so it's 1. Wait 1 sec. Let me just even do better notation. Be 1 plus cosine squared of x. That would be squared. And then, Jesus fuck, this is a mess. Let me just boop, boop, boop. And then with that, and then with this entire thing, then you would distribute, then you get cosine times 1 plus cosine squared of x. And then you would also try to solve this side. Get, you know, what is that sine of x doing there? Oh yeah, because it's the norm of the top, yeah. And then you distribute the sine of x to all that stuff. Then you distribute the minus sign. You try to find common terms and all that shit, and then do whatever you can. You see how messy that is? You see how awful that is? And like sometimes you're dealing with like 1/2. You're dealing with like more variables than this. This is a simple equation. This was simple. This is simple, and it turned into this. Interesting. Yeah, it got way worse than this because sometimes you deal with secant. The derivative of secant is secant times the tangent. That is fucking awful just because it's a derivative and you deal with 2 variables now. And then God forbid you deal with like let's say 4x. So then now you're involving even more numbers, even though you just squared it. So then you have to deal with even more numbers, more variables, sometimes you deal with more x's. The chain rule, so the quotient rule with trig functions is fucking awful. Because I would have to add these all up, distribute all of them perfectly, and then maybe if I got something, I would maybe get something like, okay, this is technically a trig. It's Pythagorean's trig identities or one of Pythagorean's identities. This is technically saying negative sine of x, right? Should be because you get if it's sine of x plus cosine of x equals 1. Should be negative sine of x. So I mean, I could do that, but I'd rather just keep it as that, even though the 1 is kind of useless to have because you would just do cosine. Yeah, but still, like it's fucking awful. And when you combine things together, you make sure you make it. Trig functions are awful. You see how simple it was? Just how simple this is and how messy it gets. And it's all because of the fucking chain rule. Anyways, sorry. Back to the video. My bad. Back to the video. That's what that's the shit that I had to do yesterday at like fucking 10 a.m. I was like, man, I gotta get this out of the way, bro.
Excuse me, sneezing.
My bad.
A product rule occurs
Don't apologize.
anytime
It's cool.
that there are 2
My
functions
bad.
multiplied to one another. And that's what's happening here, is the x is being multiplied by the y. Now, the 18 is not really a part of that mix yet, because it doesn't have to be. That 18 is sort of the coefficient sitting out front. So let's see how the derivative would work here.
Oh, just be like...
For the power rule on this one, we would just get 3x squared.
Yeah, okay.
And remember, x is the primary variable, so you can think that there's a dx there, but we don't really have to write it down. The power rule for the next one would be 6y to the first power.
dy dx.
We definitely have to insert a dy dx there. 18 is just the coefficient, like I said, and what we're going to do in this little blocked off set of parentheses.
The product rule is actually like it's pretty simple. The quotient rule, you have to do all that kind of stuff. You have to add the minus and all that shit. The good thing about the product rule is that you take the derivative of the first, which is the x, take the normal of the second, which is y, and then plus the normal of the first, which is the x, times the derivative of y. So it's of the derivative of the second. So it's really nice. And then no division too. No division. It's really nice. So this would be 1 times y plus x times y. No, x times 1. Then you would distribute and get, I don't fucking know. You would get then, I don't fucking know. Oh, Trust me, the product rule is much nicer than the quotient rule. It's just pain.
Is we're going to perform a product rule.
Let's see if I did this right.
The x is the first function and the y is the second function.
Yeah.
So here's how my mind thinks about it. The derivative of the first, well, the derivative of x would just be 1 times the regular second plus the regular first
So
times
just be
the derivative of the second.
just
Now,
be y
the
plus
derivative
x.
of y would also be 1, but since he is not the
Oh,
primary variable, we also have to attach that
shit,
dy
I forgot about that.
dx.
Okay.
That's right. It's going to come up within your product rules as well. So let's take a look one more time at what we did there. We sort of performing the motion of the product rule. We had the derivative of the first function, and he's the primary function, so he's fine the way he is, times the regular second function. Now please listen carefully. When dy dx is required is because you took a derivative that involved a y.
Okay.
At this stage in the game, we have not taken a derivative on the y value. We have simply copied him down again. It was over here when we actually took the derivative of the y value that we had to recognize that with the dy dx. So again, we have derivative of the first times the regular second plus the regular first times the derivative of the second, which is the exact amount that it required the dy dx. Now, where would I go from here? I'm going to do some basic algebra. For now, I'm going to leave the left-hand side of the equation as is, and I am going to distribute the 18 into this side. So I would wind up getting 18y.
Okay, or, make it nice notation. 18y plus 18x. Excuse me, times 18 dy dx?
Plus 18x dy dx.
Or do that.
Now we need to hit the organizing moment in our equation here.
Okay, 1 second. Let me write it down. Jeez. God, I have to take good notes and, going fast. That's okay.
So remember, that means that anything that has a dy dx on it needs to be shoved to one side of the equal sign. So I probably need to subtract that guy over right there. Subtracting over 18x
dy
dx. And anything that does not have a dy dx attached to it gets moved over to the other side. So you see me subtracting over the 3x squared. Once again, the reason why we are required to do the organization is because dy dx now shows as a common term to both of those. And we can factor that out in front.
Hold up. 18y minus 3x squared. And then when she just divides...
Lastly, this reads dy dx multiplied by a certain parenthesis unit. So if we divide...
Yep, okay, divide. That's what I kind of thought. 6y minus 18x. 6y minus 18x. So then you get dy over dx would equal 18y minus 3x squared all over 6y minus 18x. And we can't do anything because of that. She goes fast as fuck. Yeah, she does. She does, Julian, but that's okay. It's fine. I mean, I'm understanding it though. That's the weird thing. Is just like it's weird. A lot, yeah. But anyways, how are you, Julian?
By that
Look at the
same
calculus.
unit. I think we finally wind up with our final answer here.
So you can't do anything because it's a multiple.
18y minus 3x squared
and that's our slope.
Over 6y minus 18x.
This is a slope for non-function.
The last thing I would like to say,
unless
each of these coefficients can be reduced by 3. And if a question like this were to come up on the AP test anyway, it would likely be a multiple choice question.
So then it would
and they would probably go ahead and reduce each of those coefficients by 3. So the final answer would wind up looking something more like this, okay? After all of those coefficients have been divided by 3. So I think that we should do reducing like that just because it's good math, okay? But it's not that this version of the derivative was like blatantly wrong or anything. It's just a matter
even though it makes no sense because you get taught a lot. You get taught a lot in pre-calculus. You cannot touch the coefficient to an x because it's stuck to the x. And especially since it's no, you can only if they're similar, but you can touch with x squared now for some reason.
Making sure everything
good
is
math apparently.
But that is one way that the product rule.
Also, Julian, you missed my rants about using two rules inside of each other with trig functions.
How the quotient rule might show up when you're doing.
This might when I just drown myself. I don't know. Yes, good math. Yes.
Implicit differentiation.
Don't.
I have seen questions written like this before.
3x squared is equal to x minus
And just
y
by the
of
nature of the fact that the
of
right-hand
f
side of
plus
the
y.
equal sign is a quotient means that we're going to have to use the quotient rule. So let's start in on the derivative.
That's so much nicer. Okay, I got this. I got this. I'm gonna show it to you guys because I got this. Okay, hold up. So with it being 3x squared, 1 second, equals x minus y over x plus y. You get a oh. There's holes in the graph. What the fuck? There's so. Oh, that makes sense because like when you get y and y. Okay, that makes sense. They would cancel out. Yeah. Okay. So then, okay, we use the power rule. So we drop the exponent to the 3. So then it's gonna be 6x squared. 6x squared because that's the derivative. And then okay, hold up. Okay. And then I'm gonna make this a function so I can write it down much easier. And then let's just say f of x, even though I really shouldn't say f of x for this scenario, but that's okay. It's the derivative of the top, so it would be 1 minus 1 dy dx. Let me just put in correct notation. Okay. Because we took the derivative of the y. Okay. Oh wait, shit, I'm gonna have to divide. Fuck. There we go. Ah! Okay. Okay. And then times the normal of the bottom, x plus y. Minus. Remember that minus? Occasionally that minus is a very big. It's an important minus. Oh fuck. Okay, hold up. Be minus the normal of the top, x minus y, and then we would do the derivative of the top, which would be 1 plus 1 dy dx. Just fuck it. I don't care. And then all over um the bottom squared, x plus y squared. And then we would distribute, which would be I'm gonna write this on paper. Hold up. Where's another notebook? My bad. Shit. Man, my ring light hates me recently, bro. Well, I did like throw it like multiple times. not throw it, but that's okay. Okay, hold up. Fuck, I hate this. So it's me 1 minus 1 dy dx times x plus y minus x minus y. Throw it? I have not thrown it. I've like punched my desk a lot of times and like it falls over. So I mean no. Then 1 plus 1 dy dx. And then it's gonna be all over x plus y squared. Because of the ring light. My bad. Okay. This is awful distributed. Okay, so it'd be 1 times x would just be x. And then plus y. And then negative dy dx would be negative x dy dx. And then minus y dy dx. Let's make this all into one function. Minus. Is that? We know it's the. So yeah, it's x minus. Oh fuck, this is gonna be awful. Right. Oh god. Okay, hold up. And then it would be x plus x dy dx. You can't. This sucks. And then you would get negative y minus y dy dx. And then x plus y squared. Let's not make it. We can't square it, so it's going. So we want to do x plus y because like okay, we cannot do x plus y squared. Oh, what did I do? What did I do? I was so here from the beginning because then I understand maybe. Oh no, you definitely would be able to understand, especially with me trying to like I could definitely try to teach you and stuff. You would definitely understand. With x plus y squared, we can't just call it x squared plus y squared. We cannot do that. So what we have to do is that we get x. Oh yeah, yeah. Sorry, x plus y. Fuck. And then x plus, and then we would do x plus y again because of good math, good algebra. So then, oh fuck. So if it's x plus y and then x plus y, yes, the almighty teacher teach us. This is stuff that I fucking remember. So it'd be x squared plus xy, plus yx or xy. Let's just call it xy so we can combine them like terms. Plus xy, plus y squared. So then if we simplify, we get x squared plus y squared plus 2xy. Bro, fuck off! So really, this is equal to x squared plus y squared plus 2xy. Where is this function? Where's the function? Well, actually, no, it's technically not a function. Cool, it's just not there. Okay then. Okay, I gotta do the quotient rule. Okay, fuck. And then we distribute the minus sign because we just distributed that. Okay, so then we get. Okay, hold up. Let me write down the first function. X plus y minus x dy dx. Which I mean, oh wait, no, it's stuck to the coefficient. Yeah. Okay, fuck. Minus y dy dx. You put the minus sign, so then we would get negative x minus x dy dx plus y dy dx. So this cancel out that. So then so far we have y minus x dy dx minus y dy dx minus x dy dx plus y dy over dx. Hold up, I got this. I got this. It doesn't exist apparently. Yeah. Okay, hold up. Can't cancel that out. We can't cancel the negative x dy dx because they're the same term. So we get y minus y dy dx plus y dy over dx. Now, I think we could cancel the y dy over dx because they're opposite of each other. That was a mouthful and a half. Bro, like, I'm trying to do my best. Okay, so it's either, um, I'm just gonna call this top a function. Let's just say d, because I'm lazy. So it's either that it could be this, fuck, uh, dy over dx, holy shit, plus y plus y dy dx. I mean, what I could do, since technically since negative y dy over since it's negative y dy dx, I could cancel the positive y dy over dx because of it, because they're opposite of each other, so it would equal 0. You could do that. You could do that. Let's just call this. Let's just call this y. Oh, that's y. No, let's call it g because I'm late. Okay. So technically it would be so then technically we would get actually no I shouldn't do it like this so you guys can actually see the full derivative of it. Or what you could do is y plus y. So what this is really saying? Holy fuck. Okay. So really, what this is really saying is that f of x. No, I should. Fuck it. God, my bad. G of x. And we're gonna watch the video and see if I even get this right. So, well, no, okay, no, wait. This is still the quotient rule. Shit. Okay, hold up. So we get g of x is equal to I'm probably thinking y minus y of, so it's just 2y? Damn. Which one? Oh, this? Yeah, that's probably just 2. So, yeah, oh, yeah, it is probably just 2y, yeah. 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 It could be 2y, or maybe I'm wrong because you don't want to get rid of the y dy dx, maybe. I don't know, or maybe I did my Schubert property wrong or something, but it's just fucking messy as all hell. So it's probably gonna be y minus y dy over dx plus y dy over dx. Oh wait, no! Hold up. I think I know how to do this. Maybe, just maybe. And then be uh x squared x squared plus y squared. Hold up. Where's my, there it is. Plus 2xy. There we go. We just did it. Yay! Oh, that's the Quotient Rule. The Quotient Rule is so mean. Especially when you do with almost not numbers. So, knowing this... Just gonna drop this... How... Actually, no, wait, no. Actually, no, wait. I think I fucked that up. No? Yeah, just be y plus y. Yeah. Okay. That... to the video.
Here, the derivative on the left can just use a normal power rule, and he's even the primary variable.
Okay, no, yeah, I did
So
that
we don't
right.
have to worry about attaching anything special to him. It would be very wise of us to wrap our numerator and denominator in parentheses here as we are working our way through our quotient rule. So we need the derivative of the top.
Oh, okay, yeah, no, okay. Minus dy dx. Yeah, okay.
Times the regular bottom minus the regular top times the derivative of the bottom.
I should say it like that. Okay, the reason she's saying it is because it's either her or in pre-calculus honors, which I don't know what fucking class is at our school, but like he made people do the song for it so you can remember the quotient rule, so then you can remember the product rule and the quotient rule by a song, even though it's super simple. It's like, oh, just derivative of the top. It's just yeah. Don't ask. Just don't ask.
All over the bottom function squared.
So it'll be x.
Now, let's take a look at, let's say as we were taking the derivative of the top right here, let's take a closer look at that. So as I was looking at that top function, I know that the derivative of x is just 1. I also know that the derivative of y is technically just 1, but again, because he's not the primary
definitely.
variable, that's why you had to attach the dy dx there. At this stage in the game, you guys, that might be a good thing to commit to memory. Whenever we see an x and we need to take the derivative, it can go straight to 1. But when we see the y and we need to take the derivative, maybe we should just take it straight to dy dx. Again, yes, technically the derivative of y is 1, but you know that you have to stick that dy dx next to it because it's not the primary variable. Okay, now, how do we go about actually not the primary variable? Okay, now,
The
how do we
fuck,
go
G?
about
Why'd you say it like
actually
that, bro?
solving this, you guys? Because remember, implicit
I'm scared.
differentiation questions are not considered done until the dy dx is completely by itself.
Yeah,
And
no.
oh my lord, do we have a lot of things that
I
we
did
need
not
to
want
do
to do
before that's
that.
going to happen.
Mark.
Right now, this entire fraction is divided by this. I might recommend multiplying both sides by that so that we're not quite dealing, so that we don't have to deal with the drama of that sitting.
The way that I did it was totally wrong, then my bad shit, homie. Oh, I'm so pissed then. Times it both sides, yeah, x plus y squared. So then you would get... I don't want to rewrite that.
Anymore, okay? So in this next step, I'm going to write it
Wait, hold up. What?
as 6x multiplied by x plus y
Yeah,
quantity
okay,
squared.
yeah. That's gonna be awful.
And then that would leave all
Ow!
of this stuff
I'm
sitting
scared.
on the right-hand side of
To
the
the end
equal
before
sign.
deleting anything,
I
apparently.
do think that we have to FOIL it out. Otherwise, we're never going to be
Well,
able to
it's kind of
separate
useless because, like, the fraction is out now. So, like, yeah.
our dy dx terms from all the other stuff. So if I FOIL, I wind up getting x plus y minus x with a dy dx stuck to it, minus y with a dy dx stuck to it. So that was me foiling out these four terms, right?
Let's see if I was in close. I think I was kind of close, maybe. Kind of close. Kind of. I was pretty close, I think.
Here. Then I have a giant
Oh!
subtraction sign,
That explains it.
which is going to need to be applied to whatever it is I get when I FOIL all of this stuff together.
Okay.
So that's why I'm kind of separating it with
Explains
a big
everything.
chunky set of
I
parentheses
forgot
there,
about the
so that
second
I don't
distributive.
forget to go back and distribute that subtraction sign right
Excuse
there.
me. Yeah, so Julian, the one thing that I hate with the quotient rule is that you would first do the derivative. No, sorry. You first, for some reason, do the distributive property of this kind of stuff, and then with that final thing, then you would distribute the minus sign.
There.
It's one thing that like that kind of confuses me because like when you learn about the formal definition of a derivative, you automatically distribute the minus sign. So in this, I'm like, ah, oh, fuck. You got like you got to distribute the minus sign later on. You first combine you first combine and then you distribute the minus sign. The fuck why? It's just okay. The thing is, it just works. I don't know why, but it's because of just how it works. So
But for right now,
yeah,
my
you
focus
gotta
and my
distribute it
concentration is just on foiling those last two parentheses units
Oh,
together.
what a
And
stroke.
if I did that, I would get
But
x
yeah.
plus x dy dx minus y minus y
That's how it would be
dy
sometimes,
dx.
yeah.
Okay, we're getting somewhere with this. There's so much notation on my screen, you guys, that it's better to be safe than sorry.
Yeah.
So I'm going to go ahead and rewrite.
Fuck. I wrote that wrong. Yeah, no. Doesn't make sense to me to make sense, yeah.
Stuff here. And as I distribute that subtraction sign, I'm going to rewrite that stuff as well. So I get, let me just double check something. Good. So as I distribute, I'm going to get minus x dy dx plus y dy dx. So again, that was this subtraction sign.
We love the quotient rule. It's just mean.
Being applied to all of these things, okay? Alrighty, I do believe some stuff cancels here, you guys, after doing all of those extensions and expansions. This x and that negative x disappear. This negative y dy dx and this positive y dy dx also disappear. So let me take another pit stop here.
Oh, you do! Yes! I fucked up somewhere with the... Did I get rid of the x dy dx? I think I did by accident. Yeah, I did. Oh, I'm fucking stupid. Yeah, they're both negatives. You don't do that. My bad. Okay, my mind was right. You do cancel them because they're just opposites of each other. Ah! My bad. Oh my god, that's awesome. Yeah, okay, yeah, that's my bad. I got too hooked up, but that's okay. That's okay. Oh my god. But like, you do. That's so awesome. Pog. No, this is YouTube.
And
Just
figure
kidding.
out, kind of collect my thoughts here and figure out what I still have left over at this point. I do believe that this y and that y can be added together to give me a total of 2y. And likewise, negative x dy dx and another negative x dy dx winds up giving me negative 2x
2x dy dx.
Okay. Now I've hit the organized...
What's YouTube's Pog? I don't know, but why...
x
March?
dy dx. Okay.
Fucking that okay is so perfect.
Negative 2x dy dx. Okay. Now I've hit the organization phase,
Bro.
you guys. And I really like to try to have all of my dy dx terms on the left-hand side of the equal sign. So I think I'm going to wind up adding that guy this direction.
Yeah, so you would just...
And furthermore, anything that does not have a dy dx attached to it, so I think I'm going to wind up subtracting that guy over to this side. And if
it was 2y, right? Yeah, it is 2y because I mean you could just say plus y and then plus y, but it's, yeah, 2y.
Both of those moves.
So then you get
positive 2x dy dx
negative
on this
2x,
side,
yeah, dy,
and 2y subtracting over the 6x quantity x plus y squared, like that. Okay, so I think I've separated the terms. Okay, the last thing I need to do to get the dy dx by itself is divide both sides by 2x.
Oh yeah, because we need to get... Yeah, I forgot about that. Wait, it's not negative? Oh yeah, because you fucking minused it already. My bad. Divide by 2, divide by 2. So then you would get dy over dx is equal to 2y minus 6x x plus y squared, which then I think, and then it'd be all divided by 2, which 2x, which I think you would... but I don't think you could do that because the 6x is stuck to the x plus y squared, to the quantity.
And I do believe that my final answer would look something like this.
You bitch.
The 2 can kind of be reduced throughout.
Fuck.
Because,
bro! So then it would just be y minus... It would be y... Oh wait, no.
This has a 2 in it, and this has a 2 in it, and this also has a 2 in it. So as long as I am uniformly reducing all of those coefficients, it is possible for me to go ahead and reduce all of those 2's away.
I'm angry.
And so maybe my final answer looks something like this.
Oh yeah, divided by x.
You could also potentially use this x as a common denominator to split up, like, underneath this guy and underneath this guy. To maybe do just a little bit more reducing. But I don't know that that really offers us any additional benefit. So I might go ahead and leave.
Okay. So I was very close with this, actually. With doing this, I was kind of close. I just forgot the x, and then... This would be 2y. And then get rid of that. Yeah, okay. Man. Fuck. Okay. I was actually pretty close with, like, not knowing what to do. Well, like, you know, like you can cancel the dy dx, but that's okay. Just gonna get rid of all of that. Telling you.
My final answer for implicit differentiation.
You were close. Yeah, I was close to using the quotient rule properly, which is really nice.
Our final example here is going to use a tiny bit of a chain rule in it.
Please, just be easy. I have dealt with the whole entire yesterday using the chain rule inside of a fucking quotient rule. Oh, it makes me want to go fucking drown myself. I'm sorry.
So here is our example. It's not a huge, big deal chain rule. It's just a little chain rule, you guys.
Oh,
but I'm gonna go like that. And just for the fun of it. Okay, so I have the...
Just for the fun of it. Okay. I think I can do this. Hold up. I think I can do this. Okay. Let me just show you. Let me just try here, okay? Plus cosine of 5y is equal to 2xy. 2xy. Little funky crap! Now, fuck. So you do the chain rule, and then also... the product rule. Cancer. Okay, hold up. Well, that's an awesome graph. It's a little funky fresh. Did I do that derivative wrong? I think maybe I did or some shit. Okay, let's do this. So we have x plus cosine of 5y is equal to 2xy. Okay, one sec. I need to look back and when I did this. No, that's squared, so that's not going to work. But what about the coefficient out? I don't think you would take the derivative of the x. Oh, shit. Okay, fuck it. So you would take the derivative. Oh, wait, no. Yeah, because. Okay. It'd be. Okay, no. No, the chain rule states 1 plus cosine of 5y. Okay. And then times the derivative of cosine, which is negative sine of 5y. And then to the derivative of 5y would just be 5 equals 2xy. So then the 5 and the 1 get together. So it's technically saying 5 plus cosine of 5y minus sine of 5y. So far, I have 5 plus cosine of 5y minus sine of 5y. That is what I have so far is equal to 2xy. The fuck did I do? There's asymptotes. That's cool. Probably because of the 2xy. Okay. And then with the derivative of that. Oh wait, no. Oh. Oh no, wait, no. I fucked up. I fucked up. I took the derivative of y without doing the dy dx. Hold up. I fucked that up. That's actually wrong. That is wrong. That's wrong. Wrong. I'm wrong. 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 So technically saying times 5 dy dx. Technically, I think what I think I can do for better notation would be 5 dy dx plus cosine of 5y minus sine of 5y is equal to 2xy. And then, for the 2xy, we use the product rule, so it's going to be 2 to the brackets of the derivative of the first times the normal plus the derivative the normal times that. So then it would be 2 to the bracket of. I forgot, it's times dy dx. God damn it. I need to get that in my mindset, brother. Fuck. So then technically it'd be y plus x dy dx, which then I think would just be, okay, hold up, 5 dy dx plus cosine of 5y minus sine of 5y is equal to 2y plus 2x dy dx. And then, fuck, we can't combine the fucker. God damn it. So far, I have. Fuck, I did that wrong. So technically, so far, I have this to 2y. Yeah. 2y plus 2x dy dx. So then, what I'm thinking of doing so far, we would minus the 2x dy dx. So then we get 5 dy dx minus 2x dy dx is going to equal to negative cosine of 5y plus sine of 5y, because I'm trying to get dy dx to itself, so I minus the cosine to both sides and I added the sine to both sides, and then that would be plus 2y. And then we can equals negative cosine of 5y plus sine of 5y plus 2y. Okay, I think I got this. Hold up. Hold up. So then and then when you get dy dx to itself, so then we would undistribute it, so it's gonna be dy dx to the quantity of 5 minus 2x is equal to negative cosine of 5y plus sine of 5y plus 2y. Oh, why is that there? Why? Why did I do that? Okay, hold up. I got this. So then divide 5 minus 2x to both sides. So we get dy dx is equal to negative cosine of 5y minus sine of 5y, sorry, plus sine of 5y plus 2y, all divided by 5 minus 2x. So really I have this. It's equal to negative cosine of 5y plus sine of 5y plus 2y all over 5 minus 2x. 5 minus 2x. I can just add a slider. Huh? Well, oh wait, yeah, just take the derivative of 1. Well, technically be yeah. But that is what I have. Okay. Let's get into it. Let's see if I even got close to that. Okay. Okay.
Equation written like this, you guys, and I'm going to make some notations here. That little 5y in the parentheses right there is exactly what I'm talking about as far as triggering a chain rule. And you guys, remember what I said about this? Of all the little tiny rules and
details
that
let's see if it even was
students
good work.
Are very likely to forget in implicit differentiation. It's those sneaky little product rules every time an x is multiplied by a y. So we want to make sure that we're paying attention to both of those as we move our way through our derivative this time. Okay, so the derivative of x is 1, and he's the primary variable, so there's no extra stuff there. To do a chain rule, remember we have to start from the outside in. So derivative of cosine is negative
I fucked it up.
Then we are supposed to go back and chain on the derivative of the inside stuff. But when we do that, we need to be pretty careful about it, because the derivative of 5y is technically 5 but dx, the y is not the primary variable, you guys.
Fuck. I thought you would add the chain rule. I thought the x was in the chain rule. Fuck. God damn it. That changes the whole entire thing. Actually, no, it shouldn't change anything, so basically, you just get rid of this. Let's just act as nothing happened. How about that? So let's just see how that works.
Any time you take a derivative that involves a y,
oof.
You're going
you
to
tried,
have
don't
to
worry
stick
about
the
it.
dy dx
But like,
next to it, so
if I was right the first time, that would be so cool.
On the other side of the equal sign, the 2 is just a coefficient, and this little block here is going to set us up for our product rule, which is going to go the same way that it did in one of the earlier examples. The derivative of the first times the regular second plus the regular first times the derivative of the second. Okay? So that's what it winds up looking like.
Oh,
okay, algebraically speaking, how can we
get
get
that
this
just from
cleaned
practice?
up a little
Yeah,
bit?
it's just
How about 1
pain.
minus 5 times the sine of 5y with...
Where did you get the minus 5? Oh, I see. Oh, that's painful. Minus 5. Oh. You can do that? Oh. This is why I hate trig function. The notation for trig function is so fucking whack. Okay. Sine of 5y dy dx. God damn it.
with a dy dx dangling from the
Oh,
end of
I
it. So
hate
basically
that.
all I did there, you guys, was
Notation
just
is
move
so
the 5 as a
weird.
coefficient in front to join the minus sign. That was not that big of a deal. And then over here, I do need to do a little bit of distributing. So that's going to turn into 2y plus 2x
dy dx. Yeah.
Now we get to separate all of the pieces. This time I might choose to move the dy dx terms over to the right-hand side of the equal sign, simply because this right here is currently negative. So if I choose to add it over to the other side, while also taking this and subtracting it over to the other side, I think that I can get my equation to look a little cleaner with a little less negatives in it, you guys. So subtracting over the 2y this direction, and also
2y.
adding the 5 sine of 5y dy dx over this direction, right? It allows us to organize our equation so that the dy dx's are all on one side and everything else is on the other side.
I tried so hard, man.
Why do we do that? Because dy dx becomes a common term that we can factor out. And I would be left with 5 sine of 5y plus 2x. And lastly, we know that that reads dy dx multiplied by all of that stuff, and the only way to get rid of multiplying a bunch of stuff
Fuck, I cannot write this, bruh. No. My 5's and s's are so similar to each other. 5 sine of 5y plus 2x is equal to dy dx. Sag. That's awesome.
is to divide by a bunch of stuff, okay? So I'm a little lazy in my notation there, you guys, but basically I divided that over to the other side, and this would be my final answer in terms of the derivative, and notice that that involved both a chain rule and a product rule.
Okay, I mean, it wasn't as bad as the Quotient Rule one. That was fucking mean. 3 more videos. Bro, what? Oh, nah! No, it's gonna fucking suck. Second derivatives. Hopefully it's nice and easy. Because I know second derivatives are kind of mean sometimes. Well, especially if it's in the Quotient Rule. Through implicit differentiation. My hands are fancy.
Topic number 3 out of section 4.2.
Actually, wait, just in case. I mean, I was kind of close. It was just the fucking... Ooh. I was close. Again, I was close again, bruh.
Oh my goodness, you guys, if we thought first derivatives were fun through implicit differentiation,
Bro.
what does it mean when we have to take a second derivative through implicit differentiation? Well, we are about to find out. I have 2 examples that we're going to take a look at here.
Fucking 2 and 15? Oh, no, you got me tripping, dog.
And the notation gets pretty tricky, you guys, in how
My
a
brain has
person
stopped working. I'm here for
uses
vibes only. It makes sense.
the derivative notation in terms of dy dx and its second derivative.
I think I
So
feel
let's
this
start
shit's
out with
mean.
that, actually. Dy dx, we know, is what we call the first derivative because it says the derivative on y with respect to x.
Yes.
To get to the
dx.
second derivative,
Maybe d
it's
squared
actually
of
notated
y
like this, d2y over dx squared.
Do
And
not
I
know
think
why.
part
Oh,
of
wait, no.
the reason for that, okay, the reason for that
Excuse
is
me.
because you're basically saying, I would like to take another derivative with respect to x on the derivative that was already taken, right?
Okay, yeah.
So this says your first derivative has been taken. This says take another derivative on top of that. And literally, you guys, when you multiply those things,
You get d
on
squared
top you
y.
have two d's, that becomes d squared y. And in the bottom, you have the dx shows up twice, so it's dx squared. It's just over time, the mathematicians got lazy, and they did not wind up putting those parentheses around the denominator anymore. But that is where the sort of notation for that second derivative comes from. Do we really, really need to know that in order to operate our second derivatives implicitly?
Really nice.
Not really, but we do need to know what they look like, okay? d2y over dx squared is what we are going to call our second derivative.
Okay,
so let's
good.
go ahead and dive into our first example here. And I'm going to try to be as simple as I possibly can for the first round here.
God.
So let's go with y squared.
Never mind. I thought you said simple, bitch. Nah. I'm just kidding. That's gonna be pretty simple. Just because you can just do the power rule to get the first derivative on the first side.
2y equals 2x plus 5.
Are you about to say fucking all over? Please.
All of these are linear.
Oh, thank fucking God. I was about to fucking blow my brains out. Fucking, let's just make it simple. Quotient rule. Bitch ass fool. Okay, so it'd be 2y, or it'd be 2y dy dx plus 2 dy dx is equal to 2. And then we would get, you would get dy dx out of there, so then we would get dy dx in parentheses of 2y plus 2 is equal to 2. Divide that, divide that. So then we get dy over dx is going to equal 2y plus 2 2. It would just equal 2y, I think.
There is no crazy little product rules, quotient rules, or chain rules. So for the first derivative, this is going to be about as straightforward as it can get. Let's give it a try. Derivative of y squared would be 2y, but he's not the primary variable, so we attach dy dx. Same
Plus
thing here.
2 dy
Derivative of
dx
2y is 2, but y is not the primary variable, so
is
we
equal to
attach
2.
dy dx. Derivative of 2x is 2.
Wait one sec, which is equal to dy over dx is equal to 2y. Maybe.
He is the primary variable, so you can think in your brain there is a dx there, but you don't have to write it down. And lastly, the derivative of 5 just disappears.
Because
Also,
it's a constant
conveniently
rule.
for us, the dy dx's are already on the same side of the equal sign, so we can go ahead and factor them out.
2y plus 2, divide that.
And to get dy dx completely by itself, all we need to do is divide both sides by 2y plus 2.
Simplify it, right?
Okay? So far, that's what your first derivative looks like. I am noticing that each of those coefficients are 2's, so we can go through and reduce everything by 2 in order to make it just a little bit simpler for ourselves. And I do believe that simplifying before you launch yourself into your second derivative might be a decent idea.
Okay.
So how is that second derivative going to work itself out?
I'm gonna fucking hang myself.
The derivative of the first derivative we've learned is notated as d2y over dx squared. Now we do have a quotient rule on our hands, ladies and gentlemen, and if you
I fucking hate this bitch.
think about it, by the nature of the way that implicit differentiation functions are put together, you almost always wind up dividing over to the other side some sort of term that was sitting next to the dy dx.
You always have to get the quotient
So the
rule.
likelihood of us having a quotient rule when we're dealing with the second derivative is very, very high, because most of the first derivatives land themselves as being fractions of some sort, okay? So we can't be shocked by that. But we are going to go ahead and do a quotient rule here. The derivative of the top times the regular bottom minus the regular top times the derivative of the bottom. Technically, the derivative of the bottom is just y, but we have to stick a dy dx, or 1, I mean, but we have to stick a dy dx next to it.
Over
All over the bottom
1 plus
function squared.
squared.
Okay, so let me clean this up just a little bit. d2y over dx squared equals, clearly anything multiplied by 0 is just going to go to 0, so that part can disappear, leaving us with negative dy over dx all over the bottom function squared. Here's the thing, though, you guys, and this is a moment of don't shoot the messenger because I was not the one who made up this rule, okay? But the gods of calculus many years ago said, when you are presenting your final answer for the second derivative, you are not allowed to have the notation of the first derivative sitting inside of it. So what we have to do is we have to go back and reinsert whatever the first derivative equation was, okay? And we know that it was, it was...
That's very important to note. Hold up.
Right over here. This is the first derivative equation. So in other words, we're not allowed to call it dy dx. We have to call it...
I'm gonna fucking hang myself! Ah! Ooh! No! You probably do keep change flip or some shit, bro. Maybe not. Maybe not. I don't know. I'm gonna fucking drown myself, dude. Nah.
One over y plus 1. All over the bottom function squared. All right, we're going to do one more step of simplification here, you guys, before we call ourselves done. Let's think of the denominator as being quantity y squared plus, or 1 plus y squared over 1. That sets up a fraction divided...
Fucking knew it. Keep change flip that bitch. God damn it. So then it's going to be negative 1 over y plus 1 times 1 over x plus 1 squared. No, y plus 1, my bad.
By a fraction.
How
so we can do keep change flip. And oh my goodness, isn't it convenient that when we do that, you wind up with a y plus 1 in parentheses in your first denominator,
y plus 1 cubed,
and a y plus 1 quantity squared is your second denominator. So if you multiply those together, I believe your final answer upon simplifying this would be negative 1 over y plus 1 cubed. And I need to let you guys know that that happens a lot. When you go back and you back substitute for the original dy dx value, and then you do the whole keep change flip thing, it does wind up oftentimes combining itself in very neat and tidy ways. And so that is going to be your second derivative. A tiny reminder before we move on to our next and final derivative example in this video. You guys, these have meaning in real life, especially in terms of physics, and we've already talked about the fact
it's all fucking physics. That's all derivatives are.
Implicit curves tend to be special families of curves, things that are maybe circles, ellipses, twirly things that are not functions because they would fail the vertical line test. However, it is still possible for the math and physics people to say there is a particle moving along the curve, and I want you to tell me things about its velocity and about its acceleration. And we learned a long time ago, you guys, that first derivative is the velocity and second derivative is the acceleration. So that is definitely a real-life use in terms of implicit curves on why it is that we might need our first and second derivatives. So just try to keep that in mind. Okay. Here is our second and final example. This second derivative is going to be a tiny bit more involved than the first one was. So let's say they give us an implicit curve that looks...
Okay. Okay. Nice. Nice. Okay. Okay. Hold up. We got this. We got this. We got this. This is an easy one. This is a really easy one. So we have 2y is equal to x cubed plus sine of y, which proves a chain rule because of sine of y. So the 2y derivative, the derivative of 2y would be 2 dy over dx. Oh, wait, no. Okay, yeah, no, is equal to 3x squared plus cosine of y times dy over dx. So then we can get 2 dy over dx. I can do this, hold up. Equal to 3x squared plus cosine of y dy dx minus the cosine of both sides, so then we get 2 dy, fuck, hold up, 2 dy for dx is equal, no, fuck, I forgot that, minus cosine of y of dy dx. Why did I do it like that? Notation is weird, hold up. Is equal to 3x squared. Divide that, so then we get dy dx times 2 minus cosine of y is equal to 3x squared. Divide that, so then we get dy over dx is equal to cosine of 3x squared. So far for the first derivative, I have dy over dx is equal to 3x squared over 2 minus, oh, fuck, ooh, of 2 minus cosine of y. That's what I have for the first derivative. And then we do the double derivative, which would be d squared of y dx squared. Quotient rule that bitch. Ah, fuck, what would it be? One second, I'm gonna have to, like, rewrite it over here. 2 minus cosine of y. So then it would be the derivative of the first be 6x to the power of 1 times the normal, which would be, fuck, why did why? Of 2 minus cosine of y minus the normal, which would be 3x squared times 2 plus sine of y. Or how about this? Should be regular sine. Oh, so why is it still negative sine of x? Oh, that's my bad then. So it'd be minus sine of y. Minus sine of y, and then dy dx. That's going to be all over 2 minus cosine of y squared. So then we distribute that. No, okay. Let me just write it down. So it'd be this is what I have so far. Ah, 6x times 2. No, actually, no. Technically, let's put in parentheses for correct notation of 6x to 2 minus cosine of y minus 3x squared of 2 minus sine of y. But that makes no sense because, like, the derivative of cosine is negative. sine. So then, if it's a negative cosine, wouldn't that make it positive sine? Because two opposites make a positive? I don't fucking know. And then it's gonna be dy dx. But, okay. All over 2 minus cosine. Oh, fuck. Okay, now here comes the problem of where this notation works. Since we have dy over dx, because of what we learned from the last problem, I think we have to input the dy dx. So then we get this, which I think would just be this function right here. So then, hold up. Okay. Okay. So far, 6x 2 minus cosine of y minus 3x squared of 2 minus sine of y of 3x squared over 2 minus cosine of y. I think just for simple terms, I'm gonna keep it dy dx for right now, so that I can do the super property really nicely. So it's going to be 12x minus 6x cosine of y minus 6x squared. Oh wait, no, I don't think you can do that. 6x times 2, I think would just be, or you could just make it 12x. I don't fucking know. Okay, wait, no, put that in parentheses. Minus 3x squared sine of y of dy over dx, so then that would just be I don't want to do this one. This one's fucking mean, I think, dude. Hold up. I don't think I can do this one just because of that. Because, like, you would have to, like... I hate dealing with trig functions.
Something like this. As I march my way across the curve, trying to get a
Listen,
first derivative.
listen, chat, okay? I tried. That's all that matters, right? Is that I tried and I gave up at a point where it seemed very difficult, okay? Give me a break, okay?
Derivative of 2y is 2. We stick a dy dx next to it. X cubed is 3x squared. And derivative here would be cosine of y. Again, because we took a derivative on something that involved a y, we have to stick that
there was
dy
effort,
dx
yeah, a lot of
next to that
effort,
as well.
but like...
Now to
God
organize the
damn.
equation, I'm going to move this cosine y term over to the other side. So I have 2 dy dx minus cosine of y
I was right.
dy dx is equal to 3x squared. In the next move, we get to factor out the dy dx as a common term, leaving us with this. And then, of course, dy dx multiplied by a bunch of stuff. We get to divide a bunch of stuff on both sides. And so I believe our final answer for the first derivative would be that expression right there. Notice once again that it is a quotient. So as we move our way into our second derivative, we're going to need to make sure that we are performing a quotient.
I just need to have a fucking break. Holy fuck. Fuck the quotient rule, dude. God damn. It's annoying as fuck. Oh my god, dude. 1 second.
Quotient rule. So here we go. Notation for the second derivative is d2y.
Oh wait, actually 1 sec. And then okay, yeah, 1 second. I'm just gonna box this so it's important. It's gonna be d squared of y over dx.
Dx squared, and we have the derivative of the top times the regular bottom minus the regular top times the derivative of the bottom. Now let's think about the derivative of this bottom for a second, you guys.
Oh no!
The derivative of 2 is just going to disappear to 0.
I'm dumb as hell.
Since the derivative of cosine is negative sign, but you have the extra negative out front, I
fucking called it! Fuck you, Google! Fuck you! I'm so sorry. That was loud. But fuck you, Google. I fucking knew it. You would make it positive. I'm sorry. That's dumb as hell. What the fuck is HMS? What the fuck is this? Oh, damn, that's like months ago. Okay.
Positive.
Good shit, lol. Yeah, I fucking knew it, because it's like, wait, okay, negative cosine. The derivative of cosine is negative sine, so a negative on top of a pot. Fuck! You, Google! Fuck. God, Nick, I'm deaf. But like, oh, I'm so pissed. Because, like, I specifically said negative cosine, and Google did not see that. I specifically said negative cosine. It should make it a positive sign. I know cosine makes a negative sign. We know the slope of cosine is the same as negative sine. Fuck you, Google. I'm so pissed. Sorry.
In other words, the derivative of negative cosine would land you back at positive sine.
And then just be dy
you
dx.
also took the derivative of something that involved a y. So we need to make sure that we stick a dy dx right
then
there.
all over.
All
Take a
over
short break.
the
No!
function
I'm good.
squared. Oh my goodness.
We need to finish this.
Okay. And this, for all intents and purposes, remember, you guys, is correct. But it's this ominous thing over here on the side that they don't like in our final answers. So that means that we have quite a bit more algebraic simplification that we need to do. d2y over dx squared equals... Oh boy, I don't know if I'm going to distribute that out or not. Maybe I'll just leave it as is.
Oh, okay, yeah, that makes sense.
Minus 3x squared times the sine of y times whatever dy dx was originally equivalent to.
Oh,
so that was
awful.
3x squared over 2 minus cosine of y. Okay, so we've replaced the dy dx with its original value.
All over 2 minus cosine of y squared. Okay, x.
Okay.
Okay.
From here, I really would like us to emphasize this subtraction sign right here. Because if we can get all of this stuff to have the same denominator as all of this stuff, that's going to do us really good things, okay? Also remember that this denominator is technically over 1, and this denominator is also technically over 1. And in that particular section, you're just multiplying.
Yeah.
That's all you're doing is just multiplying a bunch of fractions.
The fuck?
Hopefully you remember that multiplying fractions is a very, very easy thing to do. And I am being very compartmentalized about what I'm doing right now, you guys. So right now, I'm really only addressing what's happening to the right-hand side of the subtraction sign in the numerator. Okay, I'm not addressing anything else right now. So I'm literally just looking at this whole group of stuff right here, recognizing that it's a bunch of fractions that just needs to be multiplied together. And that would give me, ooh, I can multiply the 3x squared and the 3x squared to give me a total of 9x to the fourth,
9x
multiplied by the sine of y over this denominator of 2 minus cosine y. Excellent. What a great way for me to kind of blend and combine those multiplication fractions together. Now, I would like this first section that is to the left of the subtraction sign to also have that same denominator. So I think I can do that if I multiply by the quantity 2 minus cosine y on top and bottom. Okay? I promise this is going to lead us somewhere good. I promise.
So then it should be 6x?
So now this also has the denominator 2 minus cosine y. And the numerator becomes 6x times 2 minus cosine y times 2 minus cosine y. Well, that means that
You just spawned that shit out of nowhere. But, like... Okay. Oh, no, actually, no, technically because it's okay, no, okay. I see how that worked. My bad, my bad. Never mind. The way she teaches sometimes, it's like, you just spawn that shit out of nowhere, bruh.
I could, collapse that and call it 2 minus cosine y squared. We're getting somewhere with this, even though it might not look like we are, you guys, because this fraction and this fraction now have the same denominator. And I know that when I'm working with common denominators, that I'm allowed to just keep that common denominator. And by the way, this big, huge denominator that came from all over the bottom, function squared, it still remains untouched. We haven't done anything with it. But across the top, we're simply going to write it as 6x quantity 2 minus cosine y squared minus 9x to the fourth times the sine of y. The very last thing we're going to do is down in the denominator, we're going to put a little 1 underneath this, so we have a fraction divided by a
Bro.
fraction. And that means that we can do keep, change, flip.
One second. Minus cosine y squared minus 9x tesseracts all over 2 minus cosine of y. Flip it, you would get times 2 minus cosine y squared under 1. So then you would get d squared y over dx squared would equal... What the fuck? Bro, what is the slope? 6x of 2 minus cosine y squared minus 9x tesseracts all over quantity 2 minus cosine y to the power of 3.
So this is kind of useless now because I did keep, change, flip. And if I multiply those things together, you guys, as is often true, sorry, I've lost some of my little twos on my notation here. Somebody fire me now. Okay. But as often happens with second derivatives under implicit differentiation, you're going to have a nice multiplied combination of these two things, which is going to lead you to the quantity 2 minus cosine y cubed, because there's one of them here and two of them here, and you are multiplying them, and the top pretty much stays the same, even though it's ugly, you guys. Even though it's ugly, we're just going to be okay with it, and we're going to leave our numerator like this. And that would be a way
Oh, I fucking forgot
to
sine y.
express the second derivative of your function. The last comment I'll make here, you guys, before we stop the video, is I have heard from many, many, many teachers who have more years of experience teaching calculus than I do, that it's not really the calculus that confuses people. It's the algebra steps that it takes to simplify your answers. And if you think about what we did here, you guys, this is really the only step of calculus that we did. We basically performed a quotient rule. Derivative of the top times the bottom minus top times derivative of the bottom all over the bottom, function squared. Past that, every stitch of headache that we had to deal with here had to do with combining fractions, getting common denominators, figuring out what can we multiply together, what can't we multiply together, right? I've heard calculus teachers say, the calculus is easy.
Yes. I literally say this to my dad all the time. It's the
hard.
algebra that's hard.
And I think
because you do, like, steps that you almost never did. And you're fucking doing very uncomfortable steps. You're doing every single thing. Uncomfortable. It's, like, new to you, maybe. Or you just have not used it. Suvi. Oh my god, it's... Yo, let's go, Suvi. What up? How are you? Let's go. Welcome to the stream. Thank you. Well, that's easy to write equations just because you just plug in zeros and shit. Let's do it. But hello, Suvi. Let's go. How are you, Suvi? Welcome, welcome. Welcome to my pain and torture, and my brain is fried right now. Writing. I'm good, and you're having a stroke again. No, it's just how I do. I just do stuff, but I'm glad to hear that you're doing good. I'm very glad to hear that. Suvi, hi. Yes, let's go. It's been a little bit, Suvi. Equations of tangents. Tangent and normal lines. Got the gang here. Yeah, true. Oh, got the gang bang here. No. Don't say that. No, Suvi. Ah. Normal lines. I'm doing with my life. Yeah, makes sense. Yeah. Fuck off. God damn. Under implicit differentiation. I'm just not gonna write that anymore.
Topic number 4 in section 4.2 of implicit differentiation has us writing equations of tangent and normal lines under implicit differentiation. I have 2 examples that I would like to go over.
For 13 minutes! God damn! Shit! 2? Fuck.
With you guys right now. And part of what I really want us to be thinking about as we're entering into these examples is the idea that implicit curves are often not functions. And so the very first curve that we are going to take a look at here happens to be this equation right here. And I hope...
I thought I was going to say 1. I was like, I know how to do this. God damn it. X squared plus y squared is equal to 25.
That everyone knows that this equation makes up a circle that is centered at the origin that has a radius of 5. So if I could be so obliged just to draw you guys a picture really quickly of that. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? The circle kind of goes something like this.
Yeah.
And this circle is made up of many, many infinite number of tiny little
5.
points, right? And if you go over to the point 3 comma negative 4, that point is in fact on the curve.
Crazy.
And if we want to write the equation of the tangent line,
y
right,
minus y naught
right
is equal to the slope times x minus x naught. The slope is m.
And we have learned the equation of the normal line, which skims right along this way, right? That would be your perpendicular line.
Yes.
These are things that we have all done before. It's just we've never really done them under implicit differentiation.
Even though the derivative is just
I'm going to pause and
for
just digress here for a second. Many of you who have had me in class before know that I have one sibling, a brother, and he's 5 years younger than I am, and he works as an aerospace engineer in real life.
Met him, he's really cool.
That's what he does for a living. And this idea of sort of analyzing tangent trajectories and perpendicular trajectories to those of satellites and things that orbit, right, is a huge part of what he does in his actual everyday job. Now, it can easily be said that there is no satellite that roams in a perfect circle, right? But we're gonna, and most of them are in an elliptical pattern.
Yeah, it has to be an ellipse because of Newton's gravitational law.
Derivatives with implicit differentiation here, we're just going to assume that it is a circle. But keep in mind that these kinds of things, like tangent and normal lines, do have huge uses in both math and physics.
Suvi, what you been doing recently?
So let me get to thinking about my tangent line. And all along so far in calculus, we have been using something called point-slope form to help us communicate.
Wait, what's with that? He looks pissed. Is he by any chance gay? It's the month of gay. I mean, yeah. So we got y minus y naught is equal to m of x minus x naught. So then, since we have the points, we can do y plus 4 is equal to the slope of x minus 3.
The equations of those tangent and normal lines. And that's not going to stop today, okay? So they already gave us the point of tangency there, so lucky us, we can go ahead and plug that in. Y minus the y part of the point equals the slope, and then x minus the x part of the point. The only thing that we don't have is the slope, and of course that's exactly what we use derivatives for.
Okay, hold up.
And this particular derivative is going to be taken under implicit differentiation.
Okay, I know how to do this. I know how to do this. Let me get it. Hold up. so let me write down x squared plus y squared is equal to 25. So dy dx is equal to 2x plus 2y dy dx is equal to 25 minus the 2x at both sides. Dy over dx is equal to 2y dy dx is equal to 25 minus 2x. I'm losing brain cells. How so, Subi? How so? I don't know how to do anything further, really. Maybe divide the two? No, wait, no, because then you need to get the dy dx to itself.
Also lucky for us, there are no weird product, quotient, or chain rules, so this derivative is going to be pretty straightforward. I believe the derivative of x squared is 2x. The derivative of y
derivative. Oh, Nick. Okay, I gotta go. Good luck. I love you. I love you too. Okay, Subi. See ya. Because I hate school. I'm not technically in school, so. Suck it, Subi. Bye. Bye, Murphy. Hope you enjoyed your stay. Thank you. So then it's just negative 2x on this side. I forgot. You gotta take the derivative of the whole entire equation.
Squared is 2y with a dy dx next to it, and 25 under the derivative is just going to disappear to 0.
Yeah.
To separate the dy dx terms from everything else, we can subtract the 2x over to the other side, and then simply divide by 2y in order to get the dy dx completely.
It's just that simple.
Of course, those 't's can also reduce top to bottom on the fraction,
x.
and so.
Excuse me. Forgot it's YouTube, not Twitch. I was gonna play the live in the background. Oh, I'm sorry about that, Suvi. I'm sorry. But no, actually, don't be. No, I'm not sorry. See that shit to Twitch, bro. Fuck Twitch, bro. Fuck that. Twitch fucking sucks, bro. I'm getting tired of that bullshit. I got fucked over multiple times, bro. That's fucking bullshit. Fucking looking head ass, bro. I'm telling you. But I'm sorry that you deal with that. But, you know. Why'd you leave Twitch, though? Okay, well, they fucked up twice. So, one of them... well, this is the main reason, but recently they added a new feature that if you're a partner and if you run 3-minute ads every hour, 3 minutes, you get 55% ad revenue instead of 50/50. But if you're an affiliate, you gotta wait till August to do the same thing. First of all, you're a small streamer. No one's gonna fucking watch 3 minutes ads. Like, that's dumb as hell. But that's besides the point. Another one. They got leaked / rumored that Twitch is gonna be taking 70% of sub revenue now. Instead of 50/50 split, they're taking 70% and the streamer gets only a 30%. So if you take the conversion factor, 50% of 499 is about 2.4999 whatever. You get and then us streamers get about 2.36. So we get like 10 less, about 10 cents less. If you take 30% of that, you only get $1.49. So you're about to get like $1.36 per sub. Most of my revenue, because of Twitch and study. Like, you see the problem there. I fucking, like, no, that's so much money. Because that's a big part of my... you know what, fuck it. I don't care. I'm gonna go against the fucking contract. Fuck you, Twitch. You fucking shitters, dude. This is all your fucking fault. Out of all my times of streaming, August 28th, I have made so much money off of fucking sub revenue. Like, we're fucking talking, about way over $200 of sub revenue. Originally, okay, $200 of sub revenue. Cut that in half practically. $100. Fuck you, Twitch. Fuck off. So much sub revenue. I have made nothing off of ads. Nothing compared to my sub revenue. Do you see the bullshit there? You're making half as much money from sub revenue. So I would make basically half of my money. I have to fucking move to YouTube and start early. I got, like, come on. I got fucked over by Mixer first, and I'm getting fucked over by Twitch. Twitch be bitching us. That's what I'm... Bro, like, come on. You see the fucking problem? I would make half as much money as I normally would. Because sub revenue is the biggest part of my money. I basically got I got depromoted practically. If this was an actual, I got depromoted. I would make half as much. Fuck you, Twitch. So I'm starting early on YouTube to try to get somewhere. Like I'm getting like I went through Mixer. I was popping off, doing good. I got shut down. I did so well on Twitch. Did so well. Worked so hard. I was comfortable on Twitch. I was popping off, making like 12 cents a day. That's okay. I'm making money at least. Now they're gonna take half my money. Yeah, big streamers, they don't care. They get thousands of subs every day. Oh no, you're not gonna make 10 million a year. You're gonna make 5 million. Oh no. But like small streamers that are trying to make it by at least or trying to make this a passion job, they fucking can't. Like, no, ad revenue sucks on Twitch. Be hopping on Val. I don't have Val, Monty, and I'm still doing fucking calculus. Spent days in Twitch watch you damn Twitch be bitchin'. That's what I'm fucking saying, bruh. Like, come on. Like, no. Like, so like I'm trying my best to try to get early on YouTube, so then I can potentially get paid on YouTube then before like before summer ends maybe. I don't know, but yeah, it's fucking awful. I hate it.
So the slope
My
that
bad.
we are dealing with is this, you guys. I'm going to also digress here for just a second because some of you who are abstract thinkers might be thinking, wow, that might just be the derivative of every circle that is centered at the origin. And I am going to have to agree because the only thing that changes in a circle centered at the origin would be the radius, and in the derivative, the radius turns to 0 anyway. So I don't know that we really care what the radius was when we talk about the derivative, right? It was sort of insignificant. So I do believe that that is a true statement.
Okay.
That any circle that is centered at the origin will wind up having this as its derivative. In any case, now let's remember the exact point of tangency, 3 comma negative 4. And they would like us to find the slope there. So I need a negative x value divided by the y value, and 2 negatives are going to wind up making a positive. So I believe that the slope we're dealing with here is 3/4.
Oh, okay, I see. I forgot to input them. I keep on forgetting about that. Like my elementary school teacher. Damn. Well, I mean, she did somewhere go to like a private school like multiple years. So I mean, maybe if you did go to it, maybe I don't. No, actually, no. She was a math teacher in private school, so maybe not. I don't fucking know. So it'd be -3 over -4, which would just be 3/4. So that's her m value.
If you guys also look at my picture over here of this tangent line that I sketched in, a positive slope of somewhere around 3/4 does seem pretty believable. You're close to a 45
Well,
degree
yeah, it's
angle,
going
but
up
maybe
too,
not
yeah.
quite, right? So a slope of 3/4 seems reasonable. And of course, to get the equation of that normal line, everything stays the same. The only thing that we have to do is an opposite reciprocal slope.
Which equal -4/3.
And that gives us the perpendicular trajectory of the object. Okay?
That's
so
nice.
Pretty cool. You guys, pretty cool.
Nice and
simple. And again,
simple.
thinking of it in terms of maybe orbiting, you know, and that kind of thing is really kind of nifty. So now,
even though if it's orbiting anywhere in space and it's attracted by some gravitational pull, it will never be in a circle because it's elliptical, but that's besides the point.
Second and final example in this video is going to take us to a curve that is much more challenging than that, okay?
I'm gonna fucking drown
so
myself.
Let's take the curve x sine of 2y equals y cosine of 2x. And the point they would like us to write the equation of the tangent line on is pi over 4 comma pi over 2. Now, ladies and gentlemen, we have no idea what this graph looks like outside of the fact that it does have x's and y's in it. There's a
I can do this. Hold up. Maybe not. I maybe do not want to do
it. It is probably not a function, that it fails the vertical line test.
Oh wait, no, you would just do the chain rule. So okay, yeah, be pretty nice and simple.
It's an implicit curve, but outside of that, we really don't know what's going on.
Sine 2y.
We can certainly still find the equations of the tangent normal lines,
times 2d
and so,
dy dx.
As is tradition here, I'm going to start building the equation of my tangent line, and I can say y minus the y part of the point.
Hold the fucking phone, bitch. Excuse me. I should not Actually, not this much little space, but that's gonna be fine. Goes m of x minus pi over 4. My voice died for a little.
The slope times x minus the x part of the point. What I don't have, as usual, is the slope. So I'm going to need to go on a hunt for that, finding the derivative. And you guys, oh my goodness, this derivative is going to be challenging.
Really?
For a few reasons. There are tiny little dots here that, of course...
Fucking product rule! Fuck, I knew it!
They're not going to emphasize for you because they don't want to give it away.
They're not coefficients.
But those dots do mean product rules. So that x is multiplied to the sine of 2y. That y is multiplied to the cosine of 2x. So we have product rules, and on top of that, these 2y's or the 2x in parentheses are also going to trigger the need for chain rules.
Fuck it. I'm not going to use this small piece of... I'm going to just go on the next side. Fuck it. X... Fuck. X times sine of 2y. No. You know it is 2y. Is equal to y times cosine of 2x. With x is equal... Not points. Shit. One second. I have to rewrite it now. God damn it. I'm sorry. 2. And so the tangent would be, yeah, y minus y naught is equal to the slope of x minus x naught, which would be pi over 4. There we go. So
let's try to watch really carefully how these derivatives play out. Consider this to be your first function, and this is your second function. Similarly, over here, this is your first function, and that is your second function.
Yeah.
We have two completely separate product rules that we need to perform here. The derivative of the first times the regular second plus the regular first times the derivative of the second. Now, as we're thinking about the derivative of the second function, we have to think of it in terms of a tiny little chain rule. Derivative of sine is cosine 2y, but its derivative, the derivative of 2y, would be 2 with a little dy dx attached to it, just like that. Not joking, that is what it looks like. Okay, similarly, let's do a product rule on the right-hand side. The derivative...
you're making me do so much bullshit.
Of the first, well, the derivative of y would be 1, but we have to stick a dy dx next to it, times the regular second, plus the regular first times... I kind of want to move this line, you guys, so that I can fit this in better. Derivative of the second function. Derivative of cosine would be negative sine of 2x, then chaining on the derivative of the inside stuff, which would be 2. This time, though, x is your primary variable, so you don't have to attach the dy dx to it.
You don't do any funky dy dx.
Oh my gosh, you guys, what a mess. Let's try to clean it up just a little bit, see if we can get rid of some of these multiplication dots and see what good that does us. This simplifies to sine of 2y. In this next one, I can bring together the x and the 2. So I can call it 2x dy cosine of 2y.
I forgot the fucking notation for fucking trig function. It's fucking annoying. Cosine of 2y of dy dx.
With a dy dx dangling on the end.
That's going to be equal to...
For the next one, I'm going to call it a cosine of 2x with a dy dx dangling on the end. And now my attention is focused on this group of stuff right here. I believe...
Ryan thing's weird, bro.
That the y and the negative sign and the 2 could all be multiplied together to give a negative 2y. And then we would have the sine of 2x on the edge there, okay? Now it's time to organize our equation. So anything that has a dy dx attached to it needs to be moved to one side. I'm going to go ahead and keep this guy here, moving this guy over. And I'm going to keep this guy here, but I've got to move that guy over in order to organize my equation. So now I have 2x cosine 2y with a dy dx attached. And I also subtract over cosine of 2x with a dy dx attached. On the other side of the equal sign, negative 2y sine of 2x stayed put, and I need to subtract over the sine of 2y.
That's fucking disgusting.
Now I can factor out dy dx as a common term, and some of you are probably getting to the point where you can kind of do these two steps a little bit in your head, right? Because we know.
Ah, shit, I forgot to replace some people. My bad. 1 second, chat. 1 second. My bad. What the fuck did you show? Okay, bet.
That after we factor out, after we pull out these dy dx terms, the rest of it is going to be left in parentheses, and those parentheses always get divided over to the other side. So if you would like to sort of shortcut that and do that 2 steps in one, I am totally in support of that. If you're not ready for that yet and you prefer to actually pull out the dy dx, take a closer look at what's being divided over to the other side and add in that extra step, totally fine. No pride, no pride, no shame, okay? Awesome. Oh my gosh, but what a crazy, messy derivative. And now I need to try to remember what the point was that they even wanted me to plug in. Let me write it down here. Pi over 4, comma, pi over 2. So our x's are going to be pi over 4s, and our y's are going to be pi over 2s. And I am going to cheat just a little bit here and just sort of superimpose them. Where?
Yeah, you that's good. How the -2 of pi over 2 of sine of 2 of pi over 4. Like, bitch, you got him. Well, maybe Matt is right. I'm just kidding. I'm sorry about. My bad. Oh, that. Love Matt. Love Matt. Love him. Let's go. Close that off, and then you would get. Oh my god, this is the fucking.
Where they belong here in our equation, so that's going to be a pi.
Yep, fucking knew it. Okay, maybe 2 of pi over 4. Pi over 4 cosine of 2 of pi over 2 minus cosine of 2 of pi over 4. Bro!
Pi over 2. This one is going to be a pi over 4.
Group album, so fuck
this one is going to be a pi over 2.
That's
and
awesome.
This one is going to be
okay,
whoa.
Just put that bitch in a calculator.
Let me see if I can kind of reason this out a little bit. These two things are just numbers, and the 2's wind up cross-reducing, so I'm left with negative pi.
Oh, my bad.
And this...
My bad. Yeah, you're right. Okay.
This would give me the sine of pi over 2. And if you think about your trig circle, the sine of pi over 2 is 1.
Yeah.
Minus this, after reducing, would give me the sine of pi, which is just 0. Oh my goodness, thank goodness something turned into 0. How about these little coefficients? They would reduce to pi over 2. And this part right here would reduce to the cosine of pi. And if we think about the cosine of pi, I think it's -1 on the trig circle. And then this one would reduce to the cosine of pi over 2, which again, thinking about the trig circle, I do believe that that is 0. So because they allowed us to plug in such easy angles, these angles are very easy to work with, it winds up reducing down to something really quite nice, you guys. Furthermore, when we divide by a fraction, we know that we can do keep, change, flip, and lo and behold, those negative pi's actually cross-cancel, and oh my gosh, the only thing you are left with is just the number 2. How anticlimactic was that, you guys, as far as a slope, as far as an instantaneous rate of change there, after all that drama that we went through, right? Our slope is simply 2, and nothing more than that. So if I'm going to build the equation...
Sorry, do you mean Brad Pitt, or do you... I do not know who Brad Pitt is, so my bad. And I do not. And even if it was Brad Pitt, no, I do not.
The official equation of my tangent line.
So then the tangent.
Y minus the y part of the point equals the slope. X minus the x part of the point, and then to get to the perpendicular to that, which is the normal line, I need to use the opposite reciprocal slope, but everything else stays the same. Wow, very cool.
Yes, Brad Pitt. Okay, yeah. I do not. I don't know. I'm a little funky. I'm gonna go drown. I really? I, come on, man. Fuck. Let's watch a daily dose of internet. You know what? Yeah, a little break. A little break. How about that? Little break. A little break. One video, just one video. Oh, bruh. What is this, bro? Okay, actually, oh my god, these are fucking short. Okay, so 2, 4, fuck it. 3, how about that? It's so fucking loud. I'm gonna go fucking die.
Hello everyone, this is your Daily Dose of Internet. This Walmart employee was not in the mood today.
Hey guys, welcome back to a new video. Today we're in a Walmart. We're gonna be
Yeah, I got one.
This person put aluminum
Bro! Bro's looking like me when I fucking have to, like, teach people, bro.
This person put aluminum foil on top of their kitchen
awesome.
counter to stop their cat from jumping up.
Bro flew a whole entire fucking meter, bro. That's awesome.
It almost looks like this one monkey is apologizing for their friend's bad behavior.
grabbed my leg.
Yeah, true. You were definitely right.
In case you weren't worried enough about your own privacy, we now have the technology to see through walls using Wi-Fi.
Oh yeah, that makes sense because their electromagnetic waves are pretty simple, and then you can just kind of like womp womp. Well, yeah, because of Poynting's theorem.
This poor guy might be a little top-heavy.
2, 1.
Motherfucker did a flip.
Do you, like, have cup holders? Oh, okay, perfect.
Dude, if you hit...
Like, have cup holders? Oh, okay, perfect.
Dude, if you hit 50...
Have cup holders? Oh,
Bro,
okay,
what
perfect.
the fuck? If you're...
Dude, if you hit 50...
They watch you. You sent me to the wall. Damn, that would suck, yeah. Let's say you don't have sex, bro.
Right
What? Oh my god! What? Oh. What?
A raccoon
That's
chased this woman
unfortunate.
and her dog inside the house.
Damn, bro.
Sit! Sit! Good boy. Good
That's
boy.
not okay. That's...
Come
Okay, then.
These two delivery guys raced each other to the front door.
Bro, what is this web... Bro, what is this? It's like 2 pixels, bro. Bro was hungry. God damn, bro was fiending. Jesus Christ. Motherfucker had nothing, bro. He saw that shit coming at him. He was like...
That is the end of this video. I really hope you enjoyed, and I'll see you guys again very, very soon. Later.
Motherfucker! What?
Smell it from upstairs.
I don't know. Can you just come and look at it?
Wait, yeah,
Hello
true.
everyone, this is
like,
your daily dose of
okay.
internet.
I didn't know the filter was on.
Oh no!
I found this video of this fish that has a medical condition that makes it difficult to swim sometimes.
Oh, literally Dory, okay.
I found a YouTuber that made a step-by-step process showing how anyone can make their own engine that runs on water.
Wow, look at that. You can use Bernoulli's equation for that and use it and apply to Bernoulli's principle. $3,000 watts, Jesus.
This cat escaped from the carrier and started running around the airplane.
What is this bloke doing, bro? He's just chilling. Yeah, he's just chilling. Can't complain about that at all.
Do not touch me. Do not go away. Get out of the road. Go away from me.
Get out of the road.
This mail delivery person totally forgot to park their truck.
Looks like a fucking human got out of that fucking trash can, bro.
Something started going down at this fast food drive-thru.
Bro, what did Wendy's do, bro? What the fuck? What did Wendy's do? What the fuck? Got the fucking
I found a cool food drive-thru.
Motherfucker brought the mop out. That's when you know it's serious, bro. Motherfucker, bro.
I found a cool program that can make anyone a skilled artist. You just draw some simple designs and the program will turn it into something beautiful.
That's awesome. That's so cool. Catch is vibing. I like that. Nah, that's too wholesome. He's just chilling, vibing. Yeah, I respect that. Respect the grinds.
That is the end of this video. I really hope you enjoyed.
Oh, one of
and
these
I'll see you
videos,
guys
that's
again
so
very
cool.
soon. Later.
People see Earth as flat, bruh. Dog loves. Oh fuck. No. I gotta watch this video.
Hello
I gotta
everyone,
do my
this is
calculus.
your daily dose of internet. One of my subscribers opened up a box of pasta and found a mouse that got stuck.
There's Remy from Ratatouille, bro. Fucking Remy.
Look at him go.
What is Remy doing, bro? Remy got lost.
Bro, you're gonna let the dog out. Shut the door.
Bro, what dog?
So her dad recently passed away
I
and
do not know why. I think it's so funny. Just the way that the fucking robot was just going at it, bro.
So
Going
her dad
fast.
recently passed away and was cremated, and she wanted to show a cool device that allows her to take her dad's ashes anywhere.
I get to take this with me wherever I want to. And
Damn. Bro, it's a smooch. God damn.
This person got a little too close to the ape enclosure at the zoo. Eventually, the ape did let go, and the guy was totally fine.
Bro
This
just
guy
wants a
wanted to see
smooch.
if he could purify the nastiest water he could find using these packets.
So I got a bunch of turd water in there. What I've got here is a puree bag and some P&G purifier of water packets. I'm gonna open that up, put that inside, slosh it around, mix it in real good. See how it's already clumping everything up? I want to add more product and see just how much
Chemistry.
more dirt is in here. Look at how much more it cleaned out with the second treatment there.
Why is there a pig's pigeon?
Bro's just vibing.
This guy was kind enough to save a kitten found on the side of the road.
Someone just. Oh no!
Oh, I remember watching these videos.
I can't take y'all.
That's
Oh my
awesome.
gosh.
I watched the TED Talk
Oh
on
my
this.
gosh, there's more. We got a kitten
So
problem.
cute, Jesus.
I'm not able to. Oh my god.
Bro, what the Oh, hell nah, bro. People are way too strong, bro. Okay,
What do you guys think this rat was trying to do?
What the rat doing? Bro, what is Remy doing?
I had no idea seals could live for this long, but this is what a 44-year-old seal looks like. That is the end of this video. I really hope you enjoyed, and I'll see you guys again very, very soon. Later.
Oh, I can do that. I do that in the gym. Okay, no need to fucking flex out here. Jesus. You know what? You know what? This is what you get. More calculus. Shut the fuck. Just shut the fuck. My bad. Oh, god damn it, bro. Fuck. Style questions. Wow, imagine being strong. Could never be me. Involving implicit difference. You punish me right now. Damn. No, I'm on time limit. So like, maybe after this video, maybe not. We can watch more Daily Dose of Internet. But I'm not punishing you. We're just gotta like do this stuff. Implicit differentiation. The first question goes as two curves. So it's most likely, what is it? No, wait, no, it's two curves. It can't be a function. Or I've never heard that fucking word. Orthogonal. Orthogonal. Excuse me. At a point. Point of intersection. I'm gonna come back in a bit. Okay, Betsubi, bet. Point of intersection. Section if they're tangents. Tangents meet at right angles, so they're normal to each other. Show that the following, Jesus Christ, that the following curves gonal. What the fuck's, bro? I can't write, bruh. And they intersect. Intersect at 1, -1. Do I ever reply to anyone's messages? I do. My bad, 1 second.
Okay, guys, here we are in our last and final topic for section 4.2 in BC Calc, and we get to do AP-style questions involving implicit differentiation. I have 3 questions that we're going to go through. The first one is fairly short, the second one is a little longer, and the third one is kind of a doozy, so I apologize in advance for the length of what's going on here, but I do think it gives us a really great view of how implicit differentiation might be used on the AP test. So here we are in question number 1. 2 curves are orthogonal at a point of intersection if their tangents meet at right angles. Show that the following curves are orthogonal when they intersect at 1, -1. So the first thing I want to point out is they've kind of given us a new vocabulary word here, you guys, orthogonal. Not that things meeting at right angles needed another vocabulary word, because of course they use the word perpendicular for that.
Or normal.
We've also seen the word normal, like the normal line to a tangent is perpendicular. And now we get to add on a third. Orthogonal is when they intersect in a perpendicular kind of manner. So let me go ahead and write down the curves for you guys. And you will notice right away, I hope, that these curves are sort of given in an implicit differentiation style. And they do, in fact, intersect at the point 1, -1, because if you plug in 1 for x and -1 for y, it gives you a true statement in both cases, okay? So we know that that is a point of intersection. Now, how do we test if their tangents meet at right angles? Well, of course, I think what we're going to be looking for is the idea of the opposite reciprocal slope, because that's what it means to be perpendicular. And of course, slope has to do with derivatives. So we're going to go ahead and take off in typical calculus manner here and do some derivatives, but we're going to be doing them under implicit differentiation. So here we use the power rule. We say 4x. Here, power rule would be 6y, but remember, he is not the primary variable, so we have to attach dy dx, and the derivative of any regular number just goes to 0. Keeping this dy dx term on the left-hand side of the equal sign and subtracting 4x over to the other side, then we can divide both sides by 6y, and reducing the fraction just because it's good math, negative 2x over 3y would be the final answer for the derivative of that first curve. In a similar fashion, let's tackle the derivative of the second curve under implicit differentiation. We would have 2y with a dy dx next to it, and then through the power rule we would also have 3x squared. And I'm going to divide both sides by 2y. This time the fraction can't really be reduced. Now, they want us to investigate whether they are orthogonal, particularly at this intersection point. So we're going to be plugging in 1 for x and negative 1 for the y's, and let's see what we wind up getting.
1 second. Okay.
If I plug in a 1 right here for x and a negative 1 right here for y, it would give me a negative divided by a negative, which would be a positive 2/3 slope. Over here, if I plug in 1 for x and negative 1 for y, it would wind up giving me a 3 over negative 2 slope. And look at that, you guys. By definition, we have an opposite reciprocal relationship with the slope right there at the point of intersection. So I think we can give ourselves a smiley face for a job well done. We have proven that the tangents meet
That's
at
a really
right
good
angles,
smiley face right there.
that the curves are orthogonal at their intersection point. Just as a side note before we move on to the next one, you guys, these actual curves, I'm sure, are curvy, okay? Like maybe one of them is looping around like this and one of them is kind of looping around like this, but basically what we just proved is that instantaneously, if you look at that instantaneous slope up against that instantaneous slope, that right there at that instantaneous moment, those tangents are perpendicular to one another. Yeah. Probably nowhere else on the curve, but right there at that moment, they are. Moving on to question number 2, you guys. We are going to be working with an implicit curve that looks something like this. And there are a lot of different things that they're going to ask us to do with this implicit curve. That's pretty standard when it comes to the AP test. In part A, they would like you to find 2 points where this graph crosses the x-axis. So let's think in our mind for just a second what it means to find places where a graph crosses the x-axis. First of all, I don't think they're talking about the slope, so I don't think this question has anything to do with the derivative. They're just simply asking us to find where does it cross the x-axis. And last time I checked, every time a graph crosses the x-axis, it's because its y value is equal to 0.
So it's just...
So that's how I'm going to kind of tackle the math on this particular question. Anytime my y value is equal to 0, that leads me to a little expression that says x squared equals 6.
So x
and
is
that
equal
tells us that
plus or
x
minus,
equals plus or minus the square root of 6
6
happens to be the 2 locations where that happens.
Bitch.
If they also wanted the y value that matches that, you could potentially plug it back into the original equation to find that, but in the interest of time, we're going to go ahead and skip that step for the moment, okay? Part B is asking you the tangent at those 2 points from up above should be parallel. What is their slope?
What is their slope?
So this time they are definitely talking about slope. So I need to take the original expression that was given to me. Remember that was x squared plus xy plus y squared is equal to 6. And I need to take a derivative of this in order to talk about the idea of slope. Okay, so here we have x squared under the power rule Oh, be really careful. It's one of those sneaky little product rules, you guys. Derivative of the first times the second, plus the first times the derivative of the second. So again, that little underlined area right there satisfies the product rule. And then I need the derivative of this, which under the power rule would be 2y, but we have to stick a dy dx next to it. And finally, the derivative of 0 is 6. Ha! I was just reminded of something, you guys. It was sort of a stupid comment that I made earlier, and I apologize for that. If we are finding 2 points where a graph crosses the x-axis, clearly that happens because your y value is equal to 0. So there are going to be times where you do have to plug the x value back in to find the matching y value, but we already knew the y value here, so I don't even know why I said that. Okay, to be continued, you guys, down here. Let's make sure that all of the terms that have a dy dx...
Okay, hold up, bitch. Hold up.
attached are on the left-hand side of the equal sign, and then we subtract over 2x and we subtract over the y value.
Okay, what the okay, hold up. Hold the fucking phone. What? Okay, just fuck it. I don't care anymore, bro. Minus y.
Then we can factor out dy dx as a common term, leaving us with this. Of course, what always happens with that parenthesis unit is it winds up getting divided over to the other side.
One fucking goddamn second! Shit!
So I do believe that this would be the final answer for our slope, okay? And they would like us to find whether or not those two slopes are parallel at those particular points where the graph crosses the x-axis. So remember from part A, that's plus or minus the square root of 6 comma 0. So let's take the time to test each of those. If I plug in the square root of 6 comma 0 to that slope that I just got, I would get negative 2 square root of 6 minus 0 over square root of 6 plus 2 times 0. Oh, I just love plugging in 0. And a lot of things wind up canceling, and the final answer that I wind up getting here is a slope of 2. Now, hopefully, when I plug in the other x-intercept, I'm going to wind up with the same result. And I probably will, but let's test it just to make sure. This time I would have negative 2 times negative square root 6.
Oh, yeah, because oh, I see, okay.
Minus 0 over negative square root 6 plus 2 times 0. And again, we just love plugging in the number 0 because it makes so many things disappear. And we have some cancellations. And so the final answer here is also negative 2. So I can lend myself a check mark here that I did a good job proving that those two slopes are in fact parallel. Okay, moving on to part C of this question. Part C says, find all points where the tangent is parallel to the x-axis. Okay, so
tangent is parallel. Okay, to x-axis. So it needs to be
let's think for a moment what it means for a tangent to be parallel to the x-axis.
The slope is 0 then.
Any graph that I might be dealing with, it doesn't matter what the graph looks like, to be parallel to the x-axis is basically code word for saying that the slope is equal to 0. Remember, I've mentioned a few times already in this course that to solve things successfully on the AP exam, it's not just about the math, but it's our ability to reason things through in a logical kind of way. And so when they say parallel to the x-axis, our brain needs to know that means a slope of 0. So I think that the math that we're going to follow is exactly that. We are going to take the slope, which is negative 2x minus y, over x plus 2y, and we're going to force that to be equal to 0. Now, in the world of fractions, you guys, a fraction can only truly be equal to 0 if its numerator is equal to 0. if the denominator were equal to 0, we would actually be dealing with undefined, and that's not what we want. So what I'm going to do is compartmentalize this so that just my numerator is set equal to 0. Adding the 2x to the other side. Dividing both sides by a negative. And you guys, this is another tricky part that comes up in implicit differentiation a lot. Basically, what we have done here is we have established a relationship that must exist between x and y in order for these horizontal tangents to exist. Now, what do I do with this information? Okay, the answer is you have to plug it back into the original expression that was given to us, which happens to be this. Again, what this is saying is as long as this particular relationship has been established, then you will be successful at finding tangents that are parallel to the x-axis. So that means every time that we see a y value, I'm going to plug in a negative 2x in its place, and then I have to kind of solve it out. Okay, so x squared minus 2x squared plus 4x squared in this case winds up being 6. Thank goodness that all of these are common terms that can just be combined together. I think I get 3x squared equals 6. Divide both sides by 3.
Hold up.
And take a square root. So x equals plus or minus 2. Again, technically, what you should do is take this x value back up to the original expression and plug it in to also find the matching y value. This time they are not necessarily 0 because...
Fucking what? Oh yeah, because of it being... Oh my god.
Because we're not dealing with x-intercepts. But again, in the interest of time, I'm not actually going to finish that out. Just know that you could plug in that number for the x values in this equation to find the y values that would match it, okay? But that would give us our answers for all points where the tangent is parallel to the x-axis. Lastly, we have part D of this question, and that says find all points where the tangent is parallel to the y-axis this time, ladies and gentlemen. So again, think about a graph and what it would take to be parallel to the y-axis essentially says that your slope would be undefined. Undefined. Okay, so that's the logic that we're going to follow here. If we want a tangent that is parallel to the y-axis, the slope has to go straight up and down. It needs to be undefined. So much like we did in part C, ladies and gentlemen, we know that the slope, or in other words, derivative of this expression, looks something like this. And we also know that if a fraction is going to be undefined, that happens because your denominator has been set equal to 0 or equals 0, okay? And so in that case, this time, I think that I will wind up getting x by itself. I could also get y by itself again if I wanted to, but this one is just like, you know, a path of least resistance, and I think this might be the better idea. Sweet. Okay. So remember again, what this does is it establishes a relationship that must exist between x and y in order for these vertical tangents to occur. And how do I then establish how to work with that as far as hard x and y values? I'm going to have to take them back to the original equation again and plug them in on a substitution. This time, every time I see an x, I'm going to plug in negative 2y in its place. So your expression would look something like this.
Yeah.
This becomes positive 4y squared minus 2y squared plus y squared. And as you guys are probably noticing, this equation is essentially working itself out almost identically to how the other equation did, but the difference is This time it is y values of the point that we land at instead of the x values. So again, if you needed to find the matching x values, which you probably would on the AP test, you would take those y values back up to this original equation and plug them in to get your matching x values. But oh my goodness, you guys. A comment on this one before we break down to our last AP style question, ladies and gentlemen, is that we don't always visually understand what we're doing or what we're finding. In fact, in this entire thing, we don't really know what the graph of x squared plus xy plus y squared equals 6 even looks like, okay? But we know enough about how to reason through what it means for tangents to be parallel to the x-axis or parallel to the y-axis that we should be able to still set up some calculus equations to help us solve it, okay? Even though I know that sometimes it feels like we're kind of walking around in the dark while the power's out, just keep using your logic to try to forge forward on these, okay? You're gonna be great. Here is our final AP style question in this video. And they would like you to find all normal lines to the curve. And I'm going to go ahead and give you that curve right now.
1 fucking second. Jesus Christ. I spelled curve wrong. Holy shit, bro.
That are parallel to the line 3x plus y equals 0. Okay. A lot of vocabulary words being thrown around here in terms of slope, you guys, because we know we want it to be parallel, but in the end, the lines that we're
bruh.
actually looking for are normal lines, okay? And so I think this is the way my logic is going to lead me on this particular question. I'm going to work on this equation here to get y by itself, and I know that if I want...
Hold the fucking phone. God damn. Shit, what the
want to maintain parallel to that, the slope that I need to keep is a slope of -3. However, what they want are the normal lines to the curve that fulfill that. And so I think in the end, the slope that I'm actually desiring in order to make that work is a slope of 1/3. Again, if we wanted to be parallel, it would be -3, but they're looking for the normal lines to the curve that are parallel to that. So I do believe that the slope that we are after here is going to be a slope of 1/3. Now we need to address the issue of slope. And that's going to come from taking the derivative of this through implicit differentiation. We do have a tiny little product rule there at the front, so please don't lose sight of that. Derivative of the first times the second, plus the first times the derivative of the second. And then we have +2. And don't lose this one, you guys. The derivative of y is technically 1, but you have to stick a dy dx next to it. Oh, it's...
My bad. Fucking times 1 times dy.
Very important that you don't just let that final term disappear.
God damn, 1 second.
Now if we organize our equation so the dy dx terms are all on the same side.
Holy fuck, bitch, calm down. Okay. So then we get x dy dx minus dy dx.
I need to subtract the y, I need to subtract the 2.
Yeah.
There is still a little 1 sitting there if you like that. Written in, I kind of like it written in. Factoring out the dy dx would leave you with this. And finally that parenthesis unit.
Okay, yeah, is equal to -y minus 2 over x minus 1. So we get dy over dx is equal to... Fuck, no, you don't do that yet. Is equal to... No, wait, yeah, you do that. Fuck. Is equal to y minus 2 over x minus 1.
Would get divided over to the other side. So overall, the slope that we are working with here is a slope that can be communicated by negative y minus 2 over x minus 1. Remember, what we're trying to do in this question is take this slope and force this thing about being a normal trajectory to the parallel line of the other blah, blah, blah thing that was up there. That's a fancy way of saying, let's try to make this slope equal to a third. So I'm going to do a little bit of cross multiplying here.
Fucking what? Okay, then.
I get negative 3y minus 6 is equal to x minus 1. I think I will add 6 to both sides.
Okay. It's equal to x plus 5.
So I wind up getting 5, and then I will divide everything.
Divide everything by 3. So then we get, or negative 3, wouldn't it be?
By 3. So negative 1/3 x minus 5.
Oh, okay, yeah.
5/3 is kind of the equation that I'm dealing with right now. Now I have to pause and ask myself, is that it? Like, am I done? Is this some sort of equation of a line that they're looking for here? But no, what this is, again, you guys, is the relationship that must exist between x and y in order for this whole normal line slope of a third to happen. And now what I have to do is I have to take that relationship and plug it back into the original expression that was given to me. Okay, so some of this is playing out an awful lot like the question that we just did a second ago. You can see the expression that communicates the relationship here is a little more advanced than it was in the previous question.
Oh, fuck, my butt, yeah.
Okay, so I am plugging in negative 1/3 x minus 5/3 everywhere I see a y value. And that's after doing some distributing. I'm going to get negative 1/3 x squared.
Okay, yeah. Fuck off. My bad. Wait, no, you probably don't want to do that.
Minus 5/3 x plus 2x. Distributing a negative will turn this positive. It will also turn that positive, and this whole thing is still equal to 0. Let me try my best to combine like terms. I would get negative 1/3 x squared, because that's the only x squared term in the mix. Then I have this guy and I have this guy, which combined together, I believe would give me negative 4/3 for the x. No. And then I also have a 2 mixed in there as well. I apologize for that. So negative 4/3 plus 2, I believe would wind up giving me 2/3. So let me correct that really quickly. Negative 2/3. I'm having bad math right now, you guys. Let me try that again. Negative 5/3 positive would be negative 4/3, but added to 2 would give me positive 2/3 x. And then added to 5/3 is the only constant term in the expression. Okay, I don't know about you, but trying to solve this either using factoring or the quadratic formula makes me pretty grumpy in the way that it's written right now. So I'm going to use some of my magic, and I'm going to multiply this entire equation by negative 3 to solve some problems for me. I get positive x squared minus 2x, and in this case, minus 5, and that whole thing is set equal to 0, and now
better.
I can breathe sort of a sigh of relief because I've gotten rid of the negative leading coefficient, and I've also gotten rid of all the fractions. Now, this does not factor, you guys, so believe it or not that we needed an extra layer to this question, but we're going to have to do the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. Let's see how this reduces. I believe I get 24 underneath the square root because a negative times a negative is a positive. And furthermore, I believe that the square root of 24 can be reduced to, oh, sorry, I was thinking about a 4 being under the root. Reduces to 2 root 6, and this whole thing is divided by 2, and since all of these coefficients are divisible by 2, I'm going to go ahead and reduce them all away. And I believe that my final answer is 1 plus or minus the square root of 6 as far as the x values are concerned. Once again, you guys, and I hope that they maybe wouldn't ask you to do this.
Holy
but,
fuck.
Oh, actually, maybe it's not all that bad. Because if we know that our x is equal to 1 plus or minus the square root of 6, remember, we have a relationship that exists between those two values. We know that y is always equal to negative 1/3 x minus 5/3. So if you take that x value and you plug it in right there, that would then allow you to communicate the matching y value of the point. It would be messy, but it would be numerical and it would certainly count.
I need to use the bathroom for like 1 second. Ah, 1 second. What's the desktop audio then for the... Yeah, no, never mind, my bad. Wait, oh. Wait, no. I'm sorry. Wait, 1 second. I don't fucking know. That's just... I need to watch more Daily News of Internet. 1 second. Actually, no. Shit. I just need to, Oh. 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 Fuck. Okay, 1 second. I need to write this down. Section 4.2. Class work. Okay, I'm just gonna like do this to like start and everything. Please work the problems in this order. Okay, my bad. 1A, 2A, 3A, and 4. Excuse me. Number 1B, then 2B, and C. Oh! Oh, okay, wait, no. Oh my fucking... Just one more video of Daily Dose of Internet before I get off and go, holy shit, bro. Two.
If you shop on Amazon,
Shut the
you should
fuck
use
up.
this tool. It's a browser extension that automatically compares.
Hello everyone, this is your Daily Dose of Internet. I found this video of this dog that apparently enjoys eating fire.
Motherfucker got...
Oh, watch out, kiddo.
Okay then.
That hurt, huh?
That's awesome.
Oh!
That's
this person
awesome?
found a rare white onion that suddenly becomes transparent when placed underwater.
Oh, that's awesome. That's so cool.
If you open up just a regular ordinary lithium battery, you'll find a long, thin lithium foil. And this is what happens when that lithium foil is placed in water.
Normally, it just fizzles a bunch and maybe lights on fire. In this foil form from the battery, though,
oh shit,
it can sometimes be a bit more reactive.
What people expect me to sound like when I say I'm from Scotland.
Oh, I'm a little laddie. How you doing? Hey, okay, here we go.
Sorry.
What I actually sound like.
Oh, I'm a wee laddie. How you doing? Hey, okay.
Back in
Jesus
2014,
Christ.
this person suffered from a stroke which made his left arm paralyzed. So his family helped make a device that allowed him to hug people for the first time in over 8 years.
Now, Cup, go over there.
Come here.
You can give him a hug.
Oh, that's awesome. I love that.
Aww. That's so sweet.
That's awesome. That's so sweet. What? No forward traction. That's awesome. Okay, dude.
So just yesterday, this guy right here went up to the Mona Lisa and threw a pie at it. The painting had a protective cover on, so the Mona Lisa wasn't actually affected in any way.
No way.
This is why I can't be a parent.
Shoot it.
Damn, that's what you get, child. Playing the banjo. Dumbass.
I went to the park the other day, and I was able to hand feed some birds.
That's awesome.
That is the end of this video. I really hope you enjoyed, and I'll see you guys again very, very soon.
Oh, that's
Later.
awesome. Okay. Later. Okay, one more, just one
Hello
more.
everyone, this is your Daily Dose of Internet.
Internet.
I'm not really sure why, but this employee at Disneyland interrupted this marriage proposal and even took the ring box. This guy was in his lawyer's office and wanted to see what would happen if he kissed a picture of his wife.
What's the matter with you? Kissing my wife? That's your wife? Who'd you think it was? And I thought that was like an actor or something. Get up and take it back. I'll take it back. Take it back.
A photographer captured some incredible footage of a drone show in Australia.
Oh, that's fucking awesome. Master Chief from Fortnite.
us can watch TV. That's my TV! No crap, that's why I'm freaking stealing it. I'm calling the cops.
This poor guy was thinking too hard.
That's why I'm freaking stealing it.
What in that response? Great, now we don't.
Great, now none of us can watch TV. That's my TV! No crap, that's why I'm freaking stealing it. I'm calling the cops.
This poor guy was thinking too hard.
That's awesome. Bro, that's easy. What do you mean?
If you take M&Ms and put them in water, the dye will start to fall off. If you leave them in water long enough, the M will actually float to the surface because it's made of paper.
Yeah. Damn. Well, the fuck has got the M. Damn, that's unfortunate.
I found this professional driver that drives using their feet.
Bro, what? Oh no, bro, what the fuck? That's so
One of my
cute.
subscribers was out scuba diving when he learned that some fish actually enjoy getting pets and a hug.
Oh, that's so cool. That's so cute.
That is the end of this video. I
That's
really hope you
awesome.
enjoyed, and I'll see you guys again very, very soon. Later.
Okay.